Hello, everyone. My name is Alex Baker, and I'd like to welcome all of our new and existing users to the Moldex3D 2024 standard training. Just a couple admin things before we get started. Please keep your microphones muted throughout this session to keep the distractions to a minimum. This session is being recorded, and the recording will be uploaded to our YouTube channel, Moldex3D North America. All attendees of this training will receive a link to watch the video at your convenience or share with your colleagues. Any questions you have may be sent through the chat section of Teams, and we will help to answer those questions live to keep everything moving along as smoothly as possible. This session is meant to be interactive, and to follow along, you'll need two things. The first thing is the Moldex3D Studio 2024. This application will be installed automatically onto your desktop. And the other thing is the consumer folder. You should have received a link to download this folder. You'll want to have it downloaded and extracted, as it contains the models and the simulation files that we're going to be using to follow along in this session. If you don't have either of these things, you can still follow along interactively, and you can review the recording at your convenience to follow along. The session is going to be broken up into three sections. The first one is going to be importing a model into Moldex3D and then running that model through CAD Doctor to remove any sort of problems with the solid geometry. Then we're going to get into meshing theory and how to set up the simulation. So what type of mesh is actually used? How do we select the material? What type of processing methods are available? And then the third section is going to be all about result interpretation. What do we do after the simulation is completed? And how do we effectively interpret the results of Moldex3Ds? All right, without any further ado, we're going to jump straight into the Moldex3D Studio 2024 application. You can open this application on your desktop. If you don't have it on your desktop, you can use the search bar to always find that application as well. All right, and when you open up Studio 2024, you're going to have four options up at the top left corner. The first two allow you to open or create a project file. And then the next two allow you to import a model as a new project or import an existing run as a new project. These are new options in 2024. Typically, we'll just be using the first two, but if you want to experiment with importing a model as a new project, you can do so as well. I'm going to hit the new button, and that will allow us to create a brand new simulation folder. This simulation folder will allow us to import all of our information into the simulation. These would include the mesh file, the material file, the process, any sort of inputs will be created in this folder and will be accessed by the simulation as it runs. The default name of the project or the simulation folder is going to be MDX project followed by today's date. You can delete that name and call it something a little bit more meaningful. If you have a bunch of projects running around with that default notation, it can get kind of confusing kind of quickly. So I'll call this BLM training with today's date. All right, and then the save location is going to be by default your working folder that was established when you first set up and installed Moldex3D. You can create any sort of subnetwork of folders in here, but you can save your folder there, or you can save your folder to the desktop. I actually recommend for this training for everybody to save their projects to the desktop, just to make it a little bit easier to access. Sometimes the MDX working folder, the working folder that was created, might not have been created by you. It might have been created by your ITN. You might not know exactly where that is. So placing the project in your desktop for the current moment is going to make things a little bit easier and a little bit smoother. All right, once you have the name and location established, you can press OK. This is going to create your simulation project. Over on the left side of the screen here is your project tree. This is where all of your inputs are going to appear. And actually, once we run the simulation, this is also where the outputs are going to appear as well. So you can see the different rows. A bunch of them are grayed out because that information is not yet available. But you can see mesh or model, material, process, analysis type, computation files, and then right below computation will be all of our outputs that we'll investigate later on. Up along the top side is what we call the ribbon of Moldex3D Studio. We're going to follow this interface from left to right until Moldex3D changes the tabs for us. So we're starting out here in the Home tab. Moldex3D is going to route us to the individual tabs as we work through this interface. It's very straightforward. As long as you just follow from left to right across this ribbon, Moldex3D will pretty much route you around the interface automatically. It's very straightforward that way. That being said, the first button over here on the left side is New Run. If you click on the dropdown, you'll see a couple of different options. We have the ability to create brand new simulation runs. Moldex3D has created the first run for us, so we don't actually have to do anything here. But if we want to create a brand new run, that's how you would do so. You can duplicate an existing simulation file. You can import a file from a different simulation project if you worked on something in the past and you want to import that to run a more comprehensive analysis or change the inputs in some way. You can import that information here. Then we have a couple of other options here as well. We have the DOE wizard, create run wizard, and process optimization wizard, which are all based on existing information files that are not currently available in the simulation project that we have. Like I mentioned, Moldex3D has created the first run for us, so we don't actually have to interact with that first button. So we're just going to move on to the right of that, which is going to be our molding type. In this training, I'm going to be going through injection molding, but you can see a bunch of different advanced processes here. The advanced processes that are available under this dropdown is dependent on your license that you have available to you. Each one of these advanced modules is enabled by a module. All right, so you can see things like microcellular injection molding or foam injection molding. We have compression molding, bioassisted injection molding, gas assisted. You can see all the options under here. But we are going to be utilizing injection molding for the time being. If you do have any specific questions about the advanced modules, you can ask those in the chat. We can go over those in the Q&A session at the end of this training. Moving on to the right of that is the meshing style. We have 3 meshing styles in Moldex3D. You might actually only see 2, which are solid and E-Design. Shell is kind of a niche meshing style. It's like a 2.5D solver. But in Moldex3D, we typically like to use 3D meshing solvers. And so we have solid, which is more commonly referred to as our boundary layer mesh. I'm going to go through in a little bit more detail how the boundary layer mesh works later on. And then E-Design is a more automatic approach. The element count ends up being pretty high for this, which leads to long computation times. So although it makes the pre-processing life a little bit easier, the simulation time is a lot longer for E-Design. So we typically stick with the default, which is solid. And then we'll move on to the right of that, which is import geometry. All right. In the import geometry, I'm going to have you route to that consumer folder that I just showed. The consumer folder will have a series of subfolders. Is actually the typical structure for a project where all of the inputs are going to be stored. And in this simulation folder, we have a CAD data folder that allows us to have all of the information, the input information kind of at our fingertips. Now this I have imported into the file manually, and you'll have to do that for the CAD data folder. It's really a good way to archive the information, all the inputs that you bring into your simulation, things like your process sheets, things like your mold file, your part file, all of these can be imported into this CAD data folder of your project. All right, and the file that we're going to be using for this simulation is called consumer.stp. Now we're going to be using a step file for this training, but if you click on the all types of files down here at the bottom, you can see all the different available file types that we can import into Moldex3D. We have PRT files from NX and Creo. You can bring in JT and Parasolid files, as well as CATIA files, and actually new in Moldex3D 2024 is the importing of SolidWorks files. So you can actually import those SLD PRTs and SLD ASMs directly into Moldex3D Studio. Now, step files are a more universal format, and the algorithm that we use for importing and determining the surface connection and all of those sorts of importing tolerances is pretty much tuned to step files. So they end up being a little bit cleaner, but that's not to say that the native CAD files are bad. They are pretty much on the same par, just the tolerancing is a little bit looser for those native CAD files. All right, so we're going to import the consumer.stp. All right, and that's going to bring the geometry in as a 3D solid geometry. You can rotate around by right-click dragging. You can actually change all of your mouse controls now up in your preferences, which is up at the top left corner of the studio window. Looks like a little gear. You can go to preferences and then customize. Oops, I'm sorry. It is in general. I'm sorry, it's in information, and then keyboard shortcuts and mouse control. You can find all of the information there, and you can actually edit a lot of the shortcuts over here as well. So if you want to have access to a little bit more shortcuts at your fingertips, you can go to the information keyboard shortcuts, and the mouse controls over here are not editable at the current moment. We are looking into making a more customizable mouse control configuration. But if you just want to know what all is used, what are the mouse controls for certain functions, you can look up here. Just as a short overview, like I said, right-click drag is typically going to be a rotate. You can also use the middle mouse click button to rotate as well. If you use the middle mouse scroll, that'll allow you to zoom in and zoom out. Left-clicking on an object selects it, turning the feature lines from blue to yellow. If you hold the Shift button on your keyboard and right-click drag, that will allow you to pan the model. And if you hold the Control button on your keyboard and right-click drag, that will allow you to zoom in and zoom out. It's a little bit more of a controlled zoom in and zoom out based on the centroid of the part. All right, now that we have imported the first model into Moldex3D, you can see that Moldex has transferred us automatically from the Home tab over to the Model tab. Whenever we go to a new tab, we're going to move all the way over to the left side. And once again, we're just going to work our way from left to right. All right, the first button here is Import Geometry. So if I wanted to import additional information, things like the runner or the cooling channels or even the entire mold design, I can import all of that information individually if you have it separated out. But you can actually have all this information in one singular file as each separate geometry imported into Moldex3D is going to be broken up. So you can actually have your part, runner, and cooling channels all in the same step file if you wanted to. And they will be imported as separate solid geometries so you can attribute them appropriately. All right, now moving to the right of import geometry is check geometry. Check geometry fundamentally checks for three things. We have free edges, tiny edges, and sharp face angles. I'm not going to pay too much attention to those because those are going to be fixed through the application that we're going to utilize, which is called CAD Doctor. When you install Moldex3D, by default, sometimes the CAD Doctor application is not installed automatically. So if you don't see this CAD Doctor application available here, or this CAD Doctor integration available here, then you may need to install CAD Doctor on your machine. And if that's the case, this model is quite friendly, so you will be able to continue on in the training, but I am going to open up CAD Doctor just to show the general procedure for how to fix a geometry if it needs to be fixed at all. Now, the nice thing about CAD Doctor is that it is a very quick application. We don't have to spend a whole lot of time in here. And really, we just use it to shore up a lot of the tolerancing that maybe there was a discrepancy in the tolerancing between Moldex3D and your CAD system. or maybe a surface came in a little bit weird. CAD Doctor will help us to shore up any sort of discrepancies without significantly changing the geometry. All right, now that we've imported our model, we have four buttons that we're going to click. The first one here is the check button over here on the left side. The check button will run a 16-step checking procedure, trying to identify any potential errors with the model. You can see things like narrow face, overlapping embedded faces, tiny curves. So just some general potential problems with the model. And these errors are not necessarily errors that were created in the CAD system, but rather they are potential errors that could, or interactions that could create surface meshing errors in Moldex3D. This isn't necessarily saying that there are, I don't know what this is, maybe like 70 errors in the model. It's not saying that at all. It's just saying that the way that the model was created, we might have difficulty meshing that in Moldex3D. These errors are separated into three levels of severity. The first of which is the critical severity. Critical errors we definitely want to fix before going back over into Moldex3D, as they are likely to cause a problem. Actually, in this model, they don't, but they are actually pretty likely to cause a problem, more likely than anything else. Serious errors we want to get rid of if we possibly can. We don't like to spend too much time on fixing in CAD Doctor, just because any manual effort spent in CAD Doctor isn't necessarily going to translate to a saving of time in Studio. And that's really what we use CAD Doctor for, is to save any frustration and any effort required to fix the surface mesh. We want that surface mesh to be cleaned automatically. And so fixing a lot of these errors really helps us to do that. But if we have to spend a lot of time in order to prevent those errors, then then it's not really worth it for us. The third category, minor errors, or the third level of severity, minor, we usually don't fix these. We don't really pay attention to them at all. They are a good indicator for where there's maybe a weird interaction in the geometry, but they're not something that I would ever spend time to fix. All right, so we hit check. The second button, actually to the right of the check button, is auto stitch. Auto stitch is directly related to the loop of free edges error. Loop of free edges will occur whenever two surfaces are disconnected from one another. So for example, if I had this surface up here and this surface down here, if they were not directly touching one another, there would be a loop of free edges between them. And in the case of two disconnected surfaces that are very close to one another, auto stitch will help us to respecify the tolerance of connection, and we'll just connect those for us automatically. There is another situation where loop of free edges will occur, and that is when a surface is completely missing. So for example, if this corner piece here was completely missing, there would be a loop of free edges, and then there's an operation in CAD Doctor to fix or to fill that hole automatically. The button to the right of the auto stitch tool, in this case, the auto stitch tool is grayed out, so we don't have to use it. To the right of the auto stitch tool is auto heal. Auto heal will attempt to fix every other error that we see. So I'm going to go ahead and use auto heal. It's going to go through the fixing kernel. And it's going to update the model. Something very important to note about this auto heal tool is that it will not significantly change the geometry in any way, or at least it's not intended to fix the geometry in any way. I shouldn't say fix. It's not intended to change the geometry in any way. So it's not going to go through and regenerate any surfaces. It's not going to go through and delete any surfaces to respecify a connection. If that sort of interaction is required, it's going to force you to do that manually, which is why there's typically some errors left over. If that's the case, then maybe you have to go and look at that interaction a little bit closer. But generally speaking, CAD Doctor does do a really good job at eliminating a majority of the errors that you would see in your model from when you initially click the check button. Now, after we've executed the auto heal function, The last button that we need to click in CAD Doctor is export. All right, this is just going to export our step file back into Moldex3D Studio. And so CAD Doctor is quite simple. We just hit check, auto stitch, auto heal, and then export. And that's pretty much all we have to do. There's not really any manual effort that I would recommend to implement on your model. Most of the time, any sort of manual effort is pretty minimal at this point in the iteration of Moldex3D Studio. Our mesher is very robust and is able to handle a lot of these complex interactions, even if they are identified in CAD Doctor as serious errors. We are able to handle them. And if any errors are left over, either they are a consequence of how the geometry was made, or they are simple enough where we can handle them very, very quickly in the mesh fixing tools. All right, now that I have utilized CAD Doctor, we can see that the geometry defects has been minimized. So free edges are kind of like the loop of free edges in CAD Doctor. Tiny edges are when we have a very small base on our geometry, which in this case, we don't have any. Yeah, if there's just like a very, very small feature line on our parts, the tiny edges will show up. And then sharp face angle is when two faces come in and form a pretty, well, I guess sharp or acute angle, which sometimes are an issue because if there isn't enough volume here, we can't really get the 3D solid mesh elements to completely fill this gap. And that we might need to open that angle up a little bit, which we can do manually if it's ever a problem. Most of the time, the mesher is able to handle that interaction though. So it's not a showstopper at all. All right, we can exit out of the fixed geometry function. And moving on to the right of that is the attribute function. So attribute allows us to define what this solid geometry is supposed to do in the simulation. When we import a solid geometry into Moldex3D, it's going to have this gray color, and the attribution is going to be set as none, which means that it doesn't do anything in the simulation. You can import as many models as you want to, but they don't actually mesh and they don't actually have any meaning in the simulation until you give them an attribution. All right, so I'm going to use the attribution button. It's going to ask me to select the objects to edit the attributes. So I'll left click on my part to select it. You can see that the default attribute of none comes up. I'll click on the drop down there and go to part. You'll see that the color of the geometry changes from that dark gray color to more of a beige color. And that's because each attribution has a different color associated with it. So for example, parts are the beige color, part inserts are red, cold runners are blue, and you can kind of go down through this list if you'd like to see what all of those colors are going to look like. But you'll get more familiar with those as you use Moldex3D more and more. Down here below the attribute dropdown is the user-defined group. This is actually a new feature in Moldex3D 2024, which allows you to separate different geometries from one another. For example, when I go to my model tree, we can see that the model tree here is the second tab over here on the left side of our screen. If I bring in a high cavitation tool, maybe like a 32 or 64 cavity tool, I'm going to have 64 poly surfaces that are going to be available under the part. If I wanted to separate those into maybe 8-part quadrants or 8-part groups, then I can use these user-defined groups to be able to show and hide those a little bit more conveniently. In this case, we just have a singular geometry, so no user-defined group is necessary, but know that that feature is available for any type of attribution that you create in Moldex3D. All right, we can hit close, or you can hit the escape button on your keyboard to get out of that attribution menu. And now that we have attributed our part, you can see that a bunch of other buttons have lit up. To the right of the attribution button, again, we're just going from left to right across the ribbon on the top side of our screen here. So to the right of the attribute button is model thickness, which allows us to examine the thickness distribution of our part geometry. and gets us a little bit more familiar with where the thick regions on our part are and where the thin regions on our part are. It's going to create a pretty generic mesh to start out, and then it's going to place a color distribution on top of that mesh. Some regions on your part will be identified as pretty thick. And so the color distribution by default might be a little bit skewed towards the bottom side of the part or bottom side of the scale. Over here on the right side is the scale or the color distribution. I am currently in inches, but if you wanted to switch to millimeters, you can go to your preferences menu, go to unit and number, and then you can change your unit system right here. I'm actually going to change to millimeters just to make things a little bit easier, just because I know that this part was created in metrics. All right, we can see that our scale is now in millimeters instead of inches. Now, to make it a little bit more clear what regions are thicker and which regions are thinner, you can kind of see a little bit of a difference in the color, but we want to exaggerate that color difference so that we can see really where the thick regions are in our part and where the thin regions are in our part. So I'm going to go over to my scale over here on the right side, and I'm going to left click drag the maximum on my scale and pull that down. This is a left click drag kind of on like the top of the red region of our scale. I'm going to pull that down. I'm going to keep going until we can very clearly see a difference in color between the different regions on our parts. You can see here, this guy is a little bit thicker than the nominal region on our geometry. And we can actually see that there's kind of like a thin region here as well. If I keep pulling the scale down, I can go until a major surface disappears. At that threshold, I can kind of say that this wall in this case would be about 3 millimeters thick. The nominal thickness, you can see, kind of disappears around the 2.5 millimeter range. And this guy here is maybe, it might be variable thickness actually, but maybe closer to like 2 millimeters. All right, so that's how you can utilize this tool. And this becomes a little bit more precise once you actually do get a true 3D mesh on our geometry. This splotchiness is created because of that very generic mesh that was generated when we first went into this function. So once we create a real mesh, it will replace the default mesh and give us a little bit better of a thickness distribution. All right. Now you can have this thickness distribution overlaid for the rest of your modeling if you want to use this to determine where your gate location should be, which is the next operation that we're going to do. You can certainly keep this overlaid. I personally like to get rid of it. And in order to get rid of it, you're going to go to your project tree, which is the first tab over here on the left side of your screen, the first tab over here. And you can kind of just toggle between the model, which is the colorless geometry, and the thickness. It's just very convenient that way. So you really do have access to the thickness profile whenever you want it. Moving to the right of the model thickness is our gate location determination. All right, I'm going to click on the drop down for the gate, and you can see all the different options that we have at our fingertips. All right, we have a gate location advisor, which allows us to allow Moldex3D to suggest a gate location based on the flow length ratio across the geometry. We have a nice video for how this function works over on our YouTube channel. So you can head over there if you want to learn a little bit more about how this function is utilized. I'm not going to utilize it here. I'm just going to be placing the gate manually on the geometry, either by using the add pin gate function, which is utilized more by part designers if you don't really know what type of gate is going to be used. Just adding a simple pin gate is really good for a flow study. But if you do know what type of gate is going to be used, you can utilize any of the types of gates down here. And each of them have their own parameterization associated with them. For example, an edge gate will have a rectangular cross section, whereas a pin gate will have a circular cross section, whereas a film gate will have some more parameters associated with it. Things like the distance from the main runner to the part. These sorts of parameters exist for each of these different gate types. I'm just going to use a simple pin gate here. You can either use pin gate or you can use the add pin gate function. Either one works. If you use the pin gate function, you'll be able to preview what your gate actually looks like. If you use the add pin gate function, you just kind of point and click on the part and it will create the gate normal to the geometry, kind of like what it's doing here. You just don't get the preview. All right, so I'm going to place the gate on this top surface. It's kind of like flat surface in the middle of the geometry. If you want to place the gate somewhere else on the geometry, feel free to do so. All right, and the default dimensions of this gate are going to be given by the size of the geometry and by the number of gates that you specify. All right, you can see over here in the parameterization, you can change each of the dimensions of this gate. Actually, something that's very important to note, and I'm going to make this even more of an important note when we talk about meshing. Actually, this gate that we've created is just a line, and then that line we are giving some sort of volumetric parameterization so that we can generate a solid mesh. All right, so for example, we have 3 dimensions or 3 parameters that are applied to this line. The first one is the bottom diameter, which is the red dot. You can see the red dot corresponds to the red square right here. All right, we have the green dot, which is the top diameter, and then we have the length, which is just the length of the line here. All right, so you can go in and change any of those if you want to. You can kind of preview what that gate would actually look like if you make any sort of changes to it. Gives you a nice live update. I am going to leave the defaults, but if you want to change that, feel free to do so. All right, you can close out of that attribution wizard. If you use the gate, the pin gate function here, then it will ask you to continue placing more gates. If you want to place more than one gate, you can do so. But in this case, I am just going to click the green check mark to get out of that function. You can also use the escape button on your keyboard to get out of any of those functions as well. Now, if you use the add pin gate function, you might see a red arrow on the top of your pin gate, which would indicate the melt entrance. That is where the flow simulation is going to start from. But in the case of a pin gate, when I throw a pin gate onto the part, I can also apply a runner to that pin gate, which moving on to the right of the pin gate, you can kind of see that we're still following that left to right procedure. Moving on to the right of the pin gate is the runner selection. The default parting direction is always going to be in the positive Z direction, unless you change that when you initially place the gate. And you'll note that the parting direction is kind of the direction that the melt entrance arrow is pointing. So you can see down here the axes. The Z axis is pointing towards the left side of my screen, which is towards the positive Z. All right, so in this case, we actually want the parting direction to be the negative X. You can see that this part was created with the X orientation. All right, so I want this to be the negative X, and that will pop the runner straight up into that direction. Now you can make your runner system as complicated as you would like to. I'm just going to leave it as it is right now, but you can create as many branches and whatever you want to. And you can actually do it inside of Moldex3D as well. You don't have to import all of these runner objects as a step file because, as I mentioned, the curve that or the line that we use to define the gates is also applied to the runner. You actually see that there's a center line going all the way up through the runner. So you can actually use the tool tab and the line function to just draw a bunch of lines, and then you just attribute those lines as a series of runner objects that connect to one another. All right, I'm going to keep things a little bit more simplistic for this training, but just know that you can create an entire system inside of Moldex3D. You don't really have to import everything. And actually, as it turns out, these line-defined objects that we create inside Moldex3D give us the highest quality mesh for the feed system as well as the cooling system. When we use the runner wizard, it actually creates what we call the melt entrance on the top of our runner. If you don't see this red arrow, you can use the melt entrance button, which is the button to the right of the runner function. You can also use specify point to specify where that melt entrance should be on your feed system, whether it's on the top, just on the top of your gate, if you only placed a gate, or if you created more runner lines, maybe the automatic function has a little bit of difficulty figuring out where that should be automatically. And so you might have to specify that manually. In addition, if you import your runner system, you can use the specify face function to apply more of a boundary condition to the face. This guy right here is actually just a point object. You can see that it says melt inlet node. This is actually just a point object on the top of the line that we created for our runner. If we import our geometry for our runner system instead of using these lines, then we don't really have a line to attach the point to. And so in that case, you need more of a surface boundary condition, which is where that specify face comes into play. All right, and if I wanted to just run the flow analysis and maybe even the packing analysis, this is the entire system that you need. Actually, you don't even need a runner. You could just apply the part if you're a part designer and you wanted to just see how the material is going to flow throughout your geometry. You could just throw the gate on the part somewhere and evaluate the pressure loss, evaluate the flow distribution, the flow balance, all these sorts of things. However, if we want to run the warpage analysis, if we want to actually see how this part is going to behave after it's ejected from the mold and how the dimensional stability is going to look of this geometry, we very highly recommend you to create some sort of cooling system. And now if you're a little bit upstream in the design process, you might not have the mold design created yet, but actually it is still more accurate or more appropriate to create a cooling system, kind of like a generic cooling system, just to consider the heat transfer effect from the surface of the part out to its surroundings. If we don't have any sort of cooling system, we have to assume that the entire surface of the part geometry is one singular temperature, which we define in the process. And if that's the case, then there's no differential cooling effect that's taken into account for our warpage, which, as it turns out, is one of the most important and one of the most impactful stages of our warpage analysis. All right, so we really do want some sort of cooling system. And where we'll start with that is by creating the mold base. All right, the mold base is just going to be a simple box that will encapsulate our entire system. Don't be too alarmed if the runner doesn't go all the way out to the edge of the box. It rarely does. And that's fine. For a heat transfer consideration, it's okay if this runner system if the entire melt system is contained within the box. Whereas reality, this runner might go all the way out to the surface of the box. All right, the parting direction is going to follow what we applied in either the gate wizard or the runner wizard. All right, so that should already be specified. If it is not, if it looks something like this, then you'll want to change it to the appropriate direction. This is used for clamp tonnage considerations. We want to make sure that this is in the appropriate direction. One thing to note here is the parting, kind of like a parting plane, I guess you could consider it. Although it's not really a parting plane because in Moldex3D, we don't actually separate the core and cavity sides of our mold. This is actually just one continuous block, and there is no separation between the moving side and the stationary side of our mold. This red plane here is more just used to give a visual definition of the projected area onto our mold and give us a better approximation of the clamp tonnage required to make this part. All right, so don't put too much don't mind too much if the parting plane is not necessarily in the correct direction or the correct location on the part surface. It's not that important to the analysis. All right, you can change the length, width, and height dimensions if you want to. The length and width are available here. And if you click the blue arrow up at the top, you can have access to the height dimension. I'm just going to leave everything default for this analysis. I'll press the green check mark to get out of that function. You'll actually see that that parting plane, quote unquote, goes away. And we're just left with the box and the platens that will be used to kind of visually define what our parting direction is. All right, so this gives us a good medium through which the heat can transfer, but we don't have anywhere for the heat to go. We need some sort of cooling system to extract the heat from the mold that is being released by the plastic that is continually flowing into the mold. All right, and for that, I'm going to move to the right of the mold base function, and we're going to use the cooling channels. Now, this creates a very generic cooling channel layout. And this cooling channel layout is perfectly valid as far as just a simple simulation setup. Obviously, your real mold system is going to have a more comprehensive cooling system than this, but this does allow us to consider the differential temperature effect. And at the very least, it allows us to maybe see where the heat is accumulating in our part and where we might need some conformal cooling, maybe some additional inserts, baffles, bubblers, any sort of additional cooling. We'll be able to evaluate by implementing these cooling channels in a generic array like this. Now, the cooling channel parameterization can be defined by these 5 over here. We have the channel direction. You'll see that the parting direction is grayed out. You aren't going to be able to create your cooling channels through the platens. The D parameter here is the diameter. So this allows you to increase the diameter of the cooling channels. Kind of like the runners, these are just lines. So the parameterization here is quite simplistic. You can import your cooling system as a series of step files as well, or just a singular step file to bring in these solid geometries. N is the number of cooling channels on the top and bottom. I usually leave this the default just because it gives us enough cooling channels without increasing our computation time significantly. C is the distance between these cooling channels. We want the cooling channels to pretty much spread all the way across our part geometry, and it will do that automatically for us, so we don't really have to touch this C dimension. If you want to spread them out a little bit more, you certainly could, but the default is usually pretty good. The dimension that I recommend to fix, though, or to change, I would say, is the height dimension. In our current layout, these cooling channels are a little bit too close to the surface of the geometry to where we might actually get some sort of localized cooling effect. Now, if we have enough cooling channels, then that localized cooling effect starts to diminish. But I still like to push these cooling channels a little bit further away from the part. We want these cooling channels to act as more of like a heat sink rather than as individual cylindrical heat sinks. Right, so I'd rather these be like one giant box, pretty much, right? Instead of these individual lines, I'd rather have them be one singular system. And for them to act as a singular system, we need to push them away from the geometry a little bit. My recommendation actually is to change the height dimension to be 10 times the default diameters dimension. All right, so in this case, the default diameter is 8. So the height dimension that I'm going to put in here is 80, 80. Right, like I said, pushing these cooling channels a little bit away from the surface of the part diminishes that localized cooling effect and makes these cooling channels act as almost a singular heat sink rather than as individual lines. All right, you can press the green check mark to finish out that function. And you'll actually see when you finish out that function, it creates all of the inlets and outlets on the cooling channels for you, which is actually the next button that we would go through in our nice procedure here from left to right across the top of the interface. The inlet outlet function would allow you to create those inlets and outlets automatically. But if you do use the cooling channel wizard, then it will create those inlets and outlets for you automatically anyways. eliminating the need to press this function. All right, to the right of the inlet outlet function is the check cooling system, which is going to be the last button that we click in this tab. All right, check cooling system will allow us to uh, be informed of any sort of discrepancies or any sort of problems in our geometry or in our modeling setup. Maybe the cooling channels are going through my runner, which won't happen if you use the cooling channel wizard. But if you import your cooling channels, it's very possible that your cooling channels intersect with your runner or an insert or something like that. It'll also let you know if you're missing any inlets and outlets. It'll let you know if really if there's any problems with the cooling channels in general. It's pretty smart in being able to pick up what information is necessary or what setup is necessary to create a good mesh. All right, if the cooling system is good, you'll actually get a message down here at the bottom left corner of your screen saying check cooling system okay. If you get this message, then it is good to move on to the meshing stage. But before we move on to meshing, let's take a quick break. We'll take like a 5-minute break. If you'd like to ask any questions up until this point, you can ask those in the chat section of Teams, and we'll be happy to answer those. And we'll come back at about 2:25. All right, welcome back, everyone. So in the second section of this training, we're going to go through meshing theory and setting up the simulation to run. All right, so what type of meshing styles do we use? How do we actually define the mesh in Moldex3D? As I mentioned at the beginning, we use this boundary layer meshing procedure, and we really like to use a 3D meshing approach. All right, so how does that work? And then how do we select a material, and what sort of processing parameters do we have at our fingertips? All right, so now that our model is set up, we're going to go over to the mesh tab. This is actually the only point where you have to manually click on these tabs up here. Um, if you want to access certain functions like the line tool or like, for example, the result information, you might have to click on these tools to go back and forth that way. But just as far as the general procedure goes, this is really the only point where you have to click on the one of the tabs manually. All right, so when we go over into the mesh tab, we see a few different functions. The first thing that shows up here, again, we're just going to move from left to right. The first function that we see here is the type of mesh that we're using. This isn't really something that we can interact with. This is just a reminder of what we selected back in the home tab under this dropdown right here. Moving to the right of that is what we call the node seeding. So in order to create a 3D mesh inside of Moldex3D, we create two types of meshes. The first one is the surface mesh, which is going to transform all of the surfaces on our geometries. I say geometries. In this case, it's only one single geometry. The rest of the objects in our model system right now are just a bunch of lines. But anywhere that we have a solid geometry with surfaces, what we call a polysurface object, that is going to be transformed into a series of surface mesh elements. And then from that surface mesh, we can create the mesh through the thickness, or what we call the 3D solid mesh. All right, the first thing that we're going to set up is the parameterization for our surface mesh. That's what we call the node seeding. So I'm going to click on the seeding function. It's going to ask us to select the polysurface objects, which in this case is going to be the part geometry. You could also apply this to an insert if you're looking at overmolding. If you brought your runner system in as a solid geometry, you could apply it to that. Same thing with the cooling system. But in this case, the only polysurface object that we have at our fingertips is the part. Now, the default surface mesh size that is used here is actually a pretty good value to abide by. However, we do have a more refined approach in order to determine a good mesh size number. If you just want to trust Moldex3D, you can certainly do so. For any sort of complex geometry like this, or even a little bit more complicated than this default node seeding is very, very good. But just know that if you have a simple geometry, it's kind of counterintuitive actually. If you have a more simple geometry, the default is a little bit less accurate. And the reason for that is just because there's less of a diverse array of feature line lengths. And if that's the case, then it can't really determine a good node seeding. Like if I just had a box that really only has 12 feature lines across the geometry, 4 on the top, 4 on the bottom, and then 4 on the side. And so it can't really define a good node seeding for a simple geometry. But for any sort of I'll say reasonable geometry or typical geometry, the default node seeding is pretty good. But if you want to know kind of what is the definition of a good node seeding in Moldex3D, you can follow this procedure, which we call the Goldilocks node seeding method. All right, in order to apply the Goldilocks node seeding method, we're going to have to get into a very specific viewport. First of all, I'm going to rotate my part so that I'm looking down on the top of the geometry, or down in the parting plane. Second of all, I'm going to rotate my part so that my longest dimension of my part is horizontal on my screen. All right, so I don't want my part like this. I want the longest dimension on my part to be horizontal on my screen, kind of like this. All right, and then I'm going to zoom in my geometry so that the part takes up the entire extent of the screen, either from top to bottom or from left to right, whichever one hits first. If I have a longer geometry, maybe the left to right dimension hits first, but generally speaking, I'll say maybe 80 to 90% of the time. The top to bottom dimension is what you're going to be looking for here. All right, we just want to make sure that it fills up the entire space on our screen. The reason we do this is so that we can normalize the size of the geometry to our monitor window. And a node seating is actually very consistent from model to model as long as you have this set up, or as long as you have the model oriented in that way. All right, so let's get a feel for what the node seating actually does. I'm going to hit the apply button here, and that's going to pop up all the nodes on our part geometry. All right, so each of these black nodes indicates where the surface mesh is going to start from. This is kind of like the template that the mesher uses to start creating the meshing elements. And then from there, it just kind of propagates into the middle of the surfaces. All right, so for example, if I have 3 adjacent nodes, 1, 2, 3, that's going to create a triangular surface mesh element. Next to that, we have 1, 2, 3. That's going to be a triangular surface mesh element, and it just continues on from there. Now, the value that we're applying here, in this case, 3.17 in my case, this value indicates the nominal distance between these nodes in millimeters. All right, so this is actually in millimeters, and these nodes are trying to get this far apart from one another, but they are actually constrained by a secondary parameter, and that is the length of each individual feature line. There has to be an equidistant number of nodes along that feature line. And so we can never get exactly 3.17. Actually, I guess it's technically possible, but it's extremely rare that you'll get exactly the node seating that you're looking for. What the node seating is going to do is try to get as close to this number as possible while maintaining this equidistant node constraint. This just ensures that our node seating is consistent across our geometry and across specific features of our part. All right, because this number represents the distance between the nodes, if I increase this number, that increases the distance between the nodes. And if I hit apply, we can see that that decreases the number of nodes across their geometry and increases the spacing. I can do the opposite as well. If I go down to 1, for example, I can hit apply. We can see that there's a large number of nodes that are created across the geometry. Actually, this is to the point where you can't really even see any one individual node. Our recommendation for the Goldilocks node seating is based on a very important simulation trade-off. If I have this sort of node spacing, I will have a lot of elements across my geometry, and the more elements you have on your geometry, the longer the simulation time is going to take. But conversely, actually, the more geometries you have around specific features, the better those features are defined. So if I go from a mesh size of 1 on this feature, you can see that there's a large number of nodes to define this circular object. To if I go back to the default node seating, you can actually see with the default node seating, there's only 6 nodes around the inner circumference of this boss. 1, 2, 3, 4, 5, 6. And that means that because each of these nodes are going to define kind of like a triangular surface mesh element, there's going to be a straight line from this node to this node, and from this node to this node, and so on and so forth. So this is actually going to be creating a hexagonal pattern across the inner diameter of this boss, which is not a very good approximation of this feature. And this actually carries into some of the more generic features on our geometry, and especially as we start to increase unreasonably, let's say even up to a mesh size of 10, you can start to see how some of these geometries, like this big fillet here, is just going to have an element that goes from here to here, and it ignores that fillet contour completely. So the more elements we have on our geometry, the better approximation our mesh is going to be to the original geometry. However, if we have more nodes, that means that we have a higher computation time. So it's a very important trade-off and kind of an intricate trade-off that we need to consider. And that's where this Goldilocks node seeding method comes into play. All right, let's go back to let's say 10. Actually, I'm gonna stay at 10 for now. The Goldilocks node seeding is going to be defined by the spacing between the individual nodes. You can see that each black node here has some sort of width to it. And this is actually the reason why we zoom in our part and rotate around our part to a very specific orientation, is so that we can normalize the size of our geometry to our monitor window. The relative size of these nodes is going to be the same regardless of what size of geometry you're looking at. And so if you're normalizing the part to your computer monitor or to your modeling window here, then you can really get a nice consistent node seeding approach. Our recommendation is to be able to have about 2 to 3 nodes width of space in between the individual nodes on your part. What I mean by that is I want to be able to fit about 2 to 3 of these black nodes in the space between the individual black nodes. All right, in this case, I can see that there's maybe like 5 or 6 nodes width of space. And so I would decrease my mesh size. Let's say I'll go by half. I'll go down to 5, apply. All right, I can see that there's like maybe 3 to 4 nodes width of space there. So I'll decrease just a little bit more. Okay, and actually 4 ends up being a pretty good value for this. The default value that you'll see for the node seeding is a little bit more contoured towards the geometry approximation side. So it's always going to be a little bit on the more refined side. But if you use this approach, you'll really get a more or less a perfect trade-off between the geometry approximation and simulation time. All right, so I would say that the mesh size of 4 is pretty good for this geometry. You could go maybe even a little bit larger than 4, or a little bit smaller than 4 if you're maybe wanting a little bit better geometry approximation. Don't care too much about the simulation time. If you're running the simulation overnight, maybe you don't care as much about the simulation time as much, but you still don't want it to be ridiculous. So maybe having around this value and then decrease by some amount is a procedure that I've seen a lot of users implement as well. All right, I'm going to press the green check mark now that we have our Goldilocks node seeding. And this is going to move us into what's called manual node seeding. If I rotate down to the bottom side of our part, even though we have a good Goldilocks node seeding, we can still see that some of these geometric features are not well approximated. But that doesn't mean that we can't manually go in and approximate those better. That's where this manual node seeding comes into play. So what I can do is I can go in and box select a bunch of feature lines. You can box select by left click dragging. If you go from left to right across your screen, that will select any feature lines that are contained within the box. If you go from right to left, just be careful. Going from right to left across your screen will select any feature lines that come in contact with the box. All right, so just be a little bit careful when you're using the right to left box select. It should work for most cases, but you might have to be a little bit more precise with the sizing of that box, whereas going from left to right is a little bit more generous. All right, so if I select all of the feature lines across this box, I can either specify the number of segments across each of these feature lines. In this case, I don't really want to do that because each feature line is a different length. And so if I have, let's say, 5 or 5 segments along this feature line, on this feature line is very small. That's going to create very small segments. Whereas on this feature line, which is much, much larger, those segments are going to be much larger, which is going to create a very large mesh size discrepancy across the geometry, which I don't really want to do. So I usually use the mesh size. And then I'm going to just drop this to quite a bit lower. Let's say a mesh size of 1. When you don't be too alarmed if it kind of uses a different or automatically applies a different value. The value that you apply is what each feature line is going to attempt to get to. And then the average of what each feature line actually gets to is the new value that shows up here. So don't be too freaked out if it kind of automatically changes to a different value. It will always do that. But it will still try to get to the close to the value that you initially selected. All right, and you can do this for as many feature lines as you want. So you can hold the Shift button on your keyboard to multi-select feature lines. You want to select them manually. I'm just going to do this one over here. Mesh size, and we'll do a mesh size of 1. So that automatically goes to that 0.885, which it should be very similar to this one, which is 0.883. All right, I'm going to leave this one as is just so I can contrast when we actually create the service mesh, what those end up looking like. One last thing here, when you do any sort of manual node seeding, it will change the color of the adjacent surfaces to orange. This is more for bookkeeping, just to let you know which features you have changed. So if I have, in this case, I only have 3, so it's pretty easy to remember. But if I have hundreds of these features, then I'm trying to go and manually node seed. First of all, in that case, I would just recommend going and changing the global node seeding to eliminate a bunch of time. But also, if you just have a bunch of features that you're going in and selecting, this allows you to really indicate which of those features you've actually gone in and changed already. All right, we can go ahead and press the green check mark that will get us out of the node seeding function. You'll actually see that those nodes will go away. We won't actually see those nodes come back up. But when we create the service mesh, know that the service mesher or the kernel that's used to create the service mesh is going to be directly using that template. All right, now that we've created the service mesh, now we can go in and create the solid mesh. The default parameters that are used for the solid mesh are actually pretty good at this point. However, let's go over and investigate those parameters. I'm going to skip over the generate function just so we can look at the parameterization a little bit closer. All right, so I'm going to hit the parameter button. All right, and to investigate each of these individually, I have a little bit of a slideshow just to show you how exactly the boundary layer mesh is created in Moldex3D. All right, so each region of our part has 2 bounds to it, whether this is the top bound and the bottom bound, left and right, or front and back, however you want to consider it. Every region on your part has 2 bounds to it in order to create an enclosed solid geometry. What we just did is we created the node seeding, which is used to define the service mesh. The nodes that are created across our geometry are also going to be used to create the solid mesh through the thickness. That's what we're looking at here is the top surface and the bottom surface. You can consider it, we're looking through the thickness of our geometry. Each of those surfaces, the top surface and the bottom surface, has their own node seeding applied to them. Maybe there's a logo on the bottom side that isn't on the top side. Maybe there's a rib or a boss, like we just saw on the geometry that we're working with, that occurs on one side that doesn't occur on the other side. So you can see that the nodes aren't perfectly aligned with one another. What we're going to do is we're going to extrude the nodes downwards from the top surface and upwards from the bottom surface to create a 3-layer structure. The upper and lower layers are called the boundary layers, and this middle layer is called the tetra layer. Now, typically, we are going to subdivide these layers. Our recommendation is to do a 5-layer boundary layer mesh. That's what this would be considered as. We have 5 layers on the top, 5 layers on the bottom, and then at least 1 layer of tetrahedral elements through the middle. Actually, in an ideal world, we would be able to extrude these nodes all the way from the top surface to the bottom surface. But in order to do that, we would have to have the exact same node array between the top surface and the bottom surface, which just really isn't possible for any reasonable geometry. Maybe for something like a plaque or a dog bone or some sort of regular shaped object, that would be possible. But for any sort of real geometry, you really won't have the same contour across the top surface as you do on the bottom surface of your geometry. All right, so these nodes are going to be offset from one another, which means they need to be connected. These extruded layers need to be connected, and that's where the tetra layer comes into play. It's kind of like the glue that allows you to combine these two extruded layers. Now there's three types of elements that are used in the boundary layer meshing. I'll say there's three element types that are used in Moldex3D. The first of which is the tetrahedral element. That's where the tetra layer gets its name from. These tetrahedral elements are kind of like a four-sided triangular element. They're very flexible, which makes them really good as connector elements, but they're also really good for structural analysis as well. So you'll actually see this type of element quite commonly in structural analysis or any sort of high deformation case, like vibrations even. Prism elements are used in the boundary layer section of our mesh. These are effectively extruded triangles because that's exactly what they are. Remember, we have a triangular surface mesh array, and we're just extruding that downwards to create our solid mesh. Now, conversely to the tetrahedral elements, these prism elements are quite rigid. And so they're very, very good for flow analysis because they're regular in the flow direction. If we think of our melt entrance as being over here, or maybe somewhere over on this side of the part, the flow through the boundary layer is going to be very, very consistent, which is fantastic for a flow analysis. You'll see this quite commonly in CFD. But they do actually kind of fall flat in any sort of high deformation analysis. In molding analysis, it's fine because it's pretty low deformation. But once we start getting out of that linear elastic range, these prism elements end up being poor quality, actually, whereas they are extremely high quality for flow analysis. So we use them in Moldex3D, but actually when you get over into your structural analysis, you'll want to use something more like a tetrahedral element that's a little bit more flexible. And then the third type of element that doesn't show up in this boundary layer mesh structure, but we will see this in a moment, is the hexahedral type element. This is currently the highest quality element that is possible in simulation. It is effectively two prism elements put together. You could just think of it, instead of creating a triangular surface mesh array, if you were able to create a quadrilateral surface mesh array and then extrude that, then you get your hexahedral element. These hexahedral elements are highest quality, mostly because of the number of nodes that occurs on that particular element type. If I'm looking at the results of Moldex3D, I'm going to see a blended contour. I'm not just going to see this element be one singular color. I'm going to see a distribution of color through this volume. And that's because the information at any point in this element is interpolated from the nodes on this particular element. The more nodes there are, the more precise that interpolation is going to be. So we have four nodes over here, 6 nodes in the prism element, 8 nodes in the hexahedral element. So hexahedral elements end up being the highest quality, followed by prism, followed by tetra. And that's really good because these boundary layer elements are actually used to calculate a majority of the information. Let's look at the injection molding velocity profile. All right, plastic follows what's called fountain flow, which is kind of like a parabolic velocity profile where the velocity is highest in the middle of our part cross section and 0 on the mold surface. All right, and you might think, Alex, okay, well, we have the highest value of velocity in the middle of our tetra layer. Isn't that a really bad thing? Or isn't the tetrahedral elements poor quality? And the answer to that is yes, the tetrahedral elements are poor quality, but the fact that this is a high velocity is not really a concern. The quality of our elements is really used to determine the gradient of our velocity profile, or the change in slope of our velocity profile, not necessarily the absolute magnitude. The magnitude here is just a number, which we can calculate very easily with any sort of element type. But if we look at the change in velocity across the tetra layer, you can see I've actually been a little bit generous with how much change there is in velocity across the tetra layer versus how much velocity change there is across the boundary layer. You can see that the boundary layer mesh elements are calculating a majority or used to approximate a majority of that velocity gradient. All right, and that's why we use the meshing structure that we do. First of all, the prism elements are high quality, but they're also in an array that's very regular, which allows us to create a consistent simulation approach. And also those higher quality elements are in a location of the flow that allows us to capture this change in results. This doesn't only apply to the velocity, also things like temperature and fiber orientation. All of these sorts of results are dependent on the precision of this boundary layer mesh. All right, now as far as the parameterization goes in Moldex3D, we can define the mesh type, which is just the number of layers that we're going to get through the thickness. Usually we do use the 5 layers BLM. I think the default might be 3 layers BLM, which is fine. I think that's kind of like the minimum number that we would use. But 5 layers really gives us a little bit of added precision in calculating that gradient of the velocity profile. And especially if you're using a fiber-filled material, it's really important to get a good number of layers in there. So if you're trying to optimize simulation time, 3 layers BLM is fine. But our recommendation is actually to bump that up to 5 layers BLM to get a little bit of added precision across the thickness of the geometry. The other parameter that shows up here is called the boundary layer offset ratio. The boundary layer offset ratio is going to allow us to define how thick our boundary layer actually is. I've just kind of drawn an extrusion, but we haven't really parameterized how far that extrusion should go. The offset ratio is governed by this equation up here, which is very simple. It's T equals S times OR, where T is the boundary layer thickness. S is the mesh edge length. You can kind of think of this as the node seating. And then OR is the offset ratio, which is kind of like the scalar parameter. Actually, if you were to rearrange this equation, you would get offset ratio is a ratio between the boundary layer offset distance and the mesh edge length. So if I had an offset ratio of 1, for example, that means that my boundary layer thickness is equal to my node seating, just as an example. But visually, what that looks like, if I have a low offset ratio, that means I have a low boundary layer offset or about a low thickness, because these are proportional to one another. If I have a low boundary layer thickness, then that means the extra volume has to be compensated by the tetra layer. This starts to mean that the tetra layer gets too thick. It has too much of an impact on the results, which is not great. But on the other side, if we have too high of an offset ratio, theoretically, we could have a situation where the boundary layers overlap with one another, which is also not a good thing. This actually used to be a big worry for us and used to be a value that we would have to iterate quite extensively. But in the more recent years, we've actually implemented an algorithm that automatically dials back this overlapping mesh situation. It dials back the boundary layer offset distance automatically so that there's a minimum tetra layer kind of like this, which, as you can see, kind of looks like the diagram that we've been working off so far. And that's because that's the ideal BLM. So actually what we're going to do is we're going to force this overlapping mesh situation. We're going to increase our offset ratio as high as possible to force this overlapping mesh situation and let the meshing kernel dial back that boundary layer offset distance automatically to create the minimum tetra layer in the middle of our mesh. Now, by default, the boundary layer offset ratio might be set to automatic, which actually, as it turns out, is okay for most meshes at this point. But if you want a little bit more control over it, you can set this value to the maximum, which is 3.0. Actually, if you set this to a higher value like 10, you'll be able to see that the constraints are between 0.1 and 3.0. So we can just set that to the maximum value and let the meshing kernel figure out what the true offset ratio should be for this part. That's really what the automatic offset ratio is meant to do anyways. But this is just another way that we can apply that. So either automatic, or if you're going to use manual, use the 3.0. All right, now for the runner, we actually have a different type of meshing style that we're going to utilize. We have the curve meshing style. Remember that for the runner and also the gate, we actually created a line object, and then the volume that we see in the interface here is defined by the parameterization that we created. So because we're using center lines, we can actually create a two-dimensional profile and then just extrude that two-dimensional profile along that line to create our solid mesh. Kind of like what happens in the boundary layer mesh on the part, but it happens for the entire thickness of our solid, or for our line-defined geometry. All right, so you can see over here on the left side is that two-dimensional template. The default template that shows up here, I believe, should be the 4 inner and 5 outer layers. That's our recommendation. And I don't recommend you to change this really. The thing that I do want to point out here, though, is that we do have a pure quadrilateral two-dimensional template for our, I'll say, quote unquote, surface mesh. And so when we extrude this surface mesh, we are going to get those extremely high quality hexahedral elements, which again look like this. And in addition to them being higher quality elements, the element array is going to be perfectly regular. And because of that regularity, the element count is actually going to be reduced as well. So you get a high quality element with a really good array of those elements and a lower element count. It's just beneficial all the way across the board. And that's why we actually recommend to use line defined objects as much as possible for your runner system. Obviously, it's easier from a pre-processing standpoint. It's easier to import the runner system. And there's definitely situations where the geometry of the runner is complex enough to where we can't really approximate the geometry adequately using lines. And so in that situation, you would want to use the solid geometry of the runner. But if it's possible to approximate your runner system as a series of lines, we recommend to do so because of the mesh that's created. All right, and the same thing actually applies to the cooling channels. The cooling channels are a bunch of center lines as well. And if you change the attribute up at the top here to cooling channels, you'll see the default meshing style that is applied. The default is our recommendation. You could increase the outer layer count, especially if you're looking at more of like a CFD style approach. You could certainly increase that outer layer count if you wanted to, but our recommendation is to keep it as it is. Now, the cool thing is once you set the parameters the first time, those become the defaults that are going to be used for the next mesh. All right, so once you apply a 5-layer BLM and a 3.0 offset ratio, once you get all these parameters kind of set in stone, then you can really bypass that parameterization going forward, and you can just trust that Moldex3D is going to create a really good quality solid mesh. The only thing that you might need to go in and edit would be the node seating if you want to apply that Goldilocks methodology. But like I mentioned, even for a complex geometry, that default node seating is usually pretty good anyways. So it really automates the process and makes your life as simple as possible. Nobody wants to sit here and worry about the quality of the mesh. The work that we've done in the last 5 years for the meshing kernel really does go a long way to, one, make the procedure as efficient as possible, but two, it also we've also put a lot of effort into the robustness of our meshing solver and the interaction between the simulation or the flow solver and the mesh that's created. All right, so you can really be confident that the solid mesh that's created in Moldex3D is really the highest quality mesh possible on the market for plastic molding simulation. All right, so now that all of our parameterization is set up, we can go ahead and generate our mesh. When we hit generate, you'll see all of the different stages of our mesh that are going to be created. So first of all, we're going to start with the surface mesh of all of our geometry objects. In this case, there's just the part. Then we're going to move on to the solid mesh of our melt system, and then the solid mesh of our cooling system. If you click on any of these sections, just as a quick note, that will place a tack. After this tacked section is completed, the mesher will stop. All right, so if you wanted to inspect the quality of the solid mesh for a particular section, you could certainly do so. All right, but I'm not going to do that here. I'm just going to go down to the bottom here and hit generate. That will allow us to create the surface mesh as well as the solid mesh across our geometry. All right, so right away you can kind of see the surface mesh across our parts. No errors here. And it's actually pretty rare that you get any sort of errors in the surface mesh unless there's something significantly wrong with the solid mesh. All right, so we can see that there's a little bit of a curvature-based refinement on this boss, which I applied. There's a little bit of a more consistent meshing approach on this boss. And then this is the unrefined boss. So you can see that it has increased the nodal count a little bit. It kind of does that automatically when it recognizes that there aren't a sufficient number of nodes. But it's still not very well approximated as far as a circular feature is concerned. All right, then it goes through and does the solid mesh of the part. You won't really be able to see that because it's inside the surface mesh. I'll kind of show you what that looks like in a moment. Then it goes on and creates the solid mesh of our runner. And one thing to note is it actually connects the solid mesh of our runner with the solid mesh of our part. So you can actually see that the nodes are perfectly connected between those two objects. And you can actually see that regular array of solid mesh. And the same thing goes with our cooling channels. You can see that two-dimensional template extruded all the way along our cooling channels. A very perfect array and the highest quality type of mesh that can be created in simulation at the current moment are these hexahedral elements. Now, the final stage here is the mold-based solid mesh generation. The mold-based solid mesh generation usually takes the longest, and don't be too afraid if it kind of sticks at 30. It just always does that. But what it's doing is it's conforming the solid mesh of our mold base to all of the objects that have already been created. So the surface mesh on the part, the solid mesh on our runner, and the solid mesh on our cooling channels, those are being copied or duplicated into our mold base. And then the mold base itself is just going to be a series of tetrahedral elements. And as it turns out, tetrahedral elements, in addition to being really flexible, are also really good at heat transfer. So being able to utilize that tetrahedral array for our mold base is actually very beneficial. And it also allows us to kind of get into all the nooks and crannies that might occur in our part geometry, maybe the interactions between our cooling channels and the system around it. The mold base is able to be created in pretty high quality that way. All right, once the mold base generates, then we can chisel the solid mesh and kind of see what Moldex3D has generated. We don't just want you to trust what happens in what we've selected as our parameterization. We don't just want you to trust that that we've created it automatically or that it has applied properly. We want you to actually be able to check that. And so if you go over to the tool tab, you don't have to do this every time, but maybe just for the first time here, we're going to go to the tool tab and chisel. The way the chisel tool works is I'm going to left click, drag a box. Any element contained within that box is going to be temporarily hidden. And so we can see the solid mesh that was created. All right, so the solid mesh in our parts, that 5-layer BLM. I went a little bit too far to get our runner in there. But you can see that I've sliced through the cooling channels, but they have that exact same template at any location along that cooling channel line, giving us a really high amount of confidence that we have the best quality mesh possible for the cooling channels. And that would also apply to the runner if you got the chisel in the right location. All right, you can hit the chisel button one more time to bring back the rest of your mesh. And then I'm going to go back to the mesh tab, and we're going to finish out our mesh by going all the way over to the right side here and hitting final check. All right, final check allows us to kind of transfer us from the meshing stage over into the simulation setup stage. The first things first, it saves our mesh file, but it also creates a new mesh file type. Generally speaking, our editable mesh file type is a .mdg file. You'll see that extension all over the place in Moldex3D when you're transferring files from one location to the other. But the mesh file that's being created here is actually an MFE file, which is used in the simulation itself. So it's kind of transforming us from a nodal array, which is used for the editing of our mesh, into more of a solid mesh element array. All right, so now it says the mesh is ready for the analysis. You can press OK, and that's actually going to transfer us from the mesh tab back to where we started in the home tab. If you remember, we left off in the home tab at the import geometry. And so we're just going to pick up where we left off. We're going to move to the right of import geometry, and we're just going to move to the right until we eventually get to hit the run button. All right, so to the right of import geometry is boundary conditions. There's a couple of important boundary conditions that you can apply here. The first one, and probably the most common one, is venting. By default in Moldex3D simulation, we assume that there is perfect venting. The air can escape wherever it needs to. However, if you want to see if the venting profile is sufficient to be able to extract all of the air from the mold, then you would want to apply some sort of venting boundary condition on every region of your part where vents are in the mold. And if the vents are not sufficient, then you'll get a short shot in the simulation. You'll actually see that the air will compress to a point where the melt front is no longer able to progress. And some additional boundary conditions are over here, but they're usually the venting boundary condition is the only thing you would set up here. If you want a little bit more information on venting, you can ask that in the chat, and I'll go into that a little bit more in the Q&A section if you would like. But we're going to move on for time's sake. To the right of the boundary conditions button is the material. This is where we're going to select what material we want to use in our analysis. When you hit the material button, you'll see on the left side of your screen, you're going to be transferred over to the material tree. And I can hit where it says not specified. You can see all the recently used materials that I've created or that I've used in recent simulations. But I'm going to hit the material wizard button, and that's going to open up the interface of our material wizard, which allows me to examine the material files that I've either added to my project or my user bank. But it also allows me to access the Moldex3D material database. All right, the Moldex3D material database has about 9,000 materials and is organized by first the polymer type, then by manufacturer, and then by grade name. You can search through this database pretty easily using the search function over here on the left side. You can search for either the material type, manufacturer, or the grade name independently. And you can also search for relevant material characteristics, things like the MFI, the density, fiber content, and so on. So you can find maybe a similar material if it doesn't exist, if your specific material doesn't exist in the database. If that's the case, you can also send an email over to our support system, which I'll show the email at the end of this session. You can send an email over to our support system with the spec sheet that you're trying of the material that you're trying to apply in the simulation. And we'll use what we call the material hub cloud, which is also the MHC that we show here, that I don't have connected quite yet. This is actually a new feature in 2024. You actually have a connection to the MHC through the material wizard. But we will use the material hub cloud to suggest an alternate material for you to use in your analysis. If you already have the material tested, you can also send us the raw material data, and we can curve fit that to our numerical model and give you back a material file specifically for that information that you gave us. Note that any information that you give us is going to be assumed proprietary and will not be shared in that public database until explicit permission is given to us by the material manufacturer or whoever owns that material data. All right, finally, we do have our own material characterization capabilities over in our headquarters, which is located in Taiwan. We do have a material lab where we can characterize the material specifically for Moldex3D simulation. You'll get the raw data from the material experiments, obviously, but most importantly for Moldex3D, you will get a material file that is highly customized to the information that we would look for when running the simulation. All right, I'm just going to add the first material that shows up in the database. So this polyflam grabs material. You can right click and add the project. All right, you'll see that the material has been added to the project. Up in the project tab, you can confirm that that material has been added to the project. And you can see all of the material information across the top here. We have a nice video on our YouTube channel that goes across all of these different parameters, so I won't go over them here. If you want to get a little bit more information about what shows up in a material file, you can head over to our YouTube channel. But once you add your material to the project, you can actually just close out of the material wizard, and you'll see that that material is applied automatically in your project. All right, now that I've applied the material, you can see that the button to the right of material is lit up. Now, as far as the process goes, we have two different processing methodologies. To open up both of those processing methodologies, I'm going to click on the dropdown and hit New. All right, this is going to open up what we call the process wizard. All right, and in the process wizard, we have two processing methodologies. We have CAE mode and we have machine mode. CAE mode allows us to set up kind of like a generic simulation that would apply the parameterization that we use in CAE mode is a lot more applicable to the simulation world or just as like a generic setup. The outputs are what you would usually input into your machine in reality. All right, so this is a really good way that you can determine a good processing window or just a good way to run simulation, kind of like in the early stages of product development. Below CAE mode is machine mode. In machine mode, we're actually going to select a machine from the Moldex3D machine database. And all of the parameterization that we would use for the process will be based around that machine. All right, kind of like the material information, I do have a great video up on our YouTube channel that goes over the process methodologies. But I do actually want to show off how to select a machine in the process wizard here and some additional features that are available with the machine mode. So I'm going to have you switch to the machine mode 1 setting method. Down a little bit further, we're going to click on the machine settings dropdown, and we'll go to new. This will open up the Moldex3D machine database. You can see all of the different manufacturers of machines that we have partnered with and machine manufacturers that we have retrieved their machine information from. You'll see two different icons over here next to the machine manufacturer. The first one looks like an M. The other one looks like kind of like just the feed system of a machine. If you see a manufacturer with an M, we have partnered with them directly, and we have retrieved their interface so that we can use that interface as an input into the Moldex3D simulation. All right, so we're actually able to set up our process on the machine interface, and I'll show you that in just a moment. All right, each of these machines have their own parameterization to them. If you find a machine does not exist in the database, you can click on one that's close, and these are actually all editable. If you do edit any of these machines, they will go into your user bank automatically, and you'll be able to utilize those however you want to in the future. All right, but kind of like the material, I'm just going to use the first machine that shows up here. You can just highlight that. You can add to your user bank if you want to, but all you need to do is highlight it and press OK. It'll ask you if you want to scale the profile settings. I always click yes here. And something interesting will pop up. This is an indication of whether the machine is viable for the system that we have created. So here it says the injection machine maximum shot volume is smaller than the parts volume. This indicates that the machine is too small for the part, and I would probably want to use a larger machine. All right, I'm going to ignore that for the time being, just for simplicity's sake. But generally speaking, I would go in and select a larger machine. Now, if you selected a machine manufacturer's machine that has a machine interface, you'll see the checkbox down here at the bottom, as well as the control type. Some manufacturers have multiple controller types. If I check the machine interface checkbox and then hit next down here at the bottom right corner, we'll actually see that the interface of the machine pops up. And we're actually able to interact with this machine interface. All of the inputs that we create here will apply inputs into our typical Process Wizard interface automatically. I've seen this used in a couple of different ways. Either you can use this to maybe just create screenshots to go out to your mold floor and apply these parameters directly on the molding machine. This creates a one-to-one correlation between the simulation and reality. But you can also just use this as a way to, and you can use it the opposite way as well. You can also use it to take whatever process you have on your machine and apply that directly in the simulation. Either way, you're able to more adequately input the values into Moldex3D, and maybe in a more digestible format than what we use in the typical Process Wizard. All right, like I said, I have a video up on the YouTube channel that goes through all of these individual parameters, so I won't go into those in too much detail. But these two processing methodologies allow us to really capture any sort of simulation type or any sort of simulation methodology that you would want to use, I guess, as it applies to injection molding. Each different type of molding style or each different type of advanced molding process has its own process parameterization. Things like, let's say, gas-assisted injection molding and MuCell and all these different styles of molding have different parameterizations to them. All right, if you do have any specific questions about the process parameters, you can ask those in the chat section of Teams. However, I am going to move on by saving the process file, and then you can close out of it. Once you've created your process file, you'll actually see that all of the buttons are lit up. But we are still going to be moving from left to right. I don't just like to skip all the way to run just because because we have the availability to click on run. I'm still going to move from left to right across the interface here. So the next button to the right of process is the analysis type. With the meshing that we have created here, we have pretty much three types of analyses that we can run. We can run a simple flow analysis. I really don't need a cooling system for a simple flow analysis, but I can still run a flow analysis here if I wanted to. I can run filling and packing if I wanted to see the compressibility of the material, or the effect of the compressibility of the material in our geometry, and how the packing effect is applied from our gates throughout the rest of our geometry. But probably the most common simulation style that's used for this is our warpage analysis, which is going to be the transient analysis a little bit further down in that list. The transient analysis is our typical warpage analysis. It runs the cooling analysis first, followed by filling and packing, then an update to that cooling analysis based on what happened in filling and packing, and then it finally runs our warpage analysis. So the fact that there's two coolings here is just, it runs the first cooling without any information, just kind of like a bunch of assumptions. And then the second cooling is more of just an update of that first cooling based on what actually happened in the filling and packing. So it's just a way for us to get a little bit more of a realistic interpretation of the heat transfer in our system. All right, and then finally the warpage analysis. There is another type of warpage analysis that occurs here as well. This is the process simulation. At the current moment, we don't recommend to use the process simulation just because the simulation time is very, very long. The theory behind process simulation is actually a little bit more accurate than the transient analysis, just because the solvers are more coupled together in the process simulation style. If you want a little bit more information on the difference between those two, I can certainly provide that to you. But just know that the transient analysis is a really good trade-off between the precision of the simulation and the speed of the simulation. So if you have, let's say, an unlimited amount of computation time, let's say you're running it over the weekend, process simulation might be something you could try out. But I'll say, to make sure that your computation times are as reasonable as possible, make sure to run the transient analysis type warpage analysis. All right, and to the right of the analysis dropdown is computation. Computation allows us to modify any sort of background parameters in the analysis profile or in the solvers. I'm not going to go into too much detail as far as the computation parameters here. Actually, the default computation parameter set is pretty good by default, so we can leave that be. And then to the right of that is the run button. There's a couple of options that you have to run the analysis. We're not going to run the analysis quite yet. If you want to run the analysis after this training is completed, or overnight, or whatever you want to do, feel free to do so. If you run it right now, then the result interpretation might be a little bit slower. The rendering of the model and so on is going to be bogged down by your resources being consumed by the simulation running. So we won't run the simulation yet, but you can feel free to do so after the training. You can run the analysis directly, which will run the simulation on your local machine. You can use the computing manager. The computing manager will, well, first of all, it will queue the simulation up, and you can actually run the simulation on other machines as well. So if you have other computational resources that you want to be able to access, you can actually remote compute that the analysis. Instead of using the resources of your local machine, you can maybe use a high performance computer, or maybe just a secondary a desktop or something like that. You can remote out the computation instead of computing locally. And the last one here is batch computing. If I set up multiple runs here, for example, if I use the create run wizard to create a bunch of different runs for me, that's really what this function is used for. then I can set up all those runs ahead of time and then run them all at once using the submit batch runs, which will just allow you to check all of the analyses that you've set up and then launch those all at once rather than having to run the first one, figure out that the first one is done, then launch the second one. It just allows you to kind of queue all of these up all at once, saving a lot of time. All right, so that does it for the second section of this training. The last section is going to be more about the result interpretation, what happens after the simulation has been run, how can we adequately interpret the results of the simulation. We're going to go over that in the next hour. But before we do that, we'll take a 5-minute break and we'll continue on with the last portion of this training. All right, everybody, welcome back. And we're going to go over the result interpretation now. You can minimize or close out of the current Studio window if you'd like to. We're going to open up a new instance of Studio. All right, so I'm going to open up a new window. If you want to keep that old one open, you can feel free to do so and run that after the training is completed. But when I open up the new Studio window, instead of hitting the new button like I did before, I'm going to hit open. And I'm going to route to that consumer folder that we imported the consumer step file from. Remember, we went into the CAD data folder before. And in this consumer folder, I'm going to scroll all the way down to the bottom and find the MRM file. The MRM file is what we use to open up the simulation. But I do want to note something very important, and that's that the MRM file itself is only about 5.5 gigabytes. All right, it's very, very small. So if you're trying to, the information in this MRM file calls all of the information from the folders that exist in this project. The MRM file by itself is not the information of the project. I see a lot of users trying to transfer around this MRM file, thinking that this is all of the simulation files. It is not. It is just the file that calls all of the other information. So if you want to archive this project, you would need to archive all of these folders as well as the MRM file, not just the MRM file, just as a small note. All right, so we're going to open up the MRM file, and that's going to open up a pre-run simulation. So we're all looking at the same information here. This is a full warpage analysis. You can see the mesh that I've used for this guy is a little bit tighter than the one that we created. All right, so how can we adequately interpret the results of a Moldex3D analysis? All right, I kind of like all the other information that I've showed here. I have videos for each one of these different stages of the analysis for filling, packing, cooling, and warpage over on our YouTube channel. So if you want to go check that out, I'm going to have a QR code at the end of this session so you can find exactly where that channel is located. But I'm going to go over some of the more important result information that you need to be able to interpret in Moldex3D and kind of some of the different tools that are available at your disposal. First things first, whenever I go into result interpretation, I like to turn off the mesh. The mesh lines, although it's really nice to know what the quality of mesh looks like, they do kind of get in the way of the color contours that we're going to be trying to visualize. All right, and so I'm going to go up to the top middle of my modeling window. And the centermost button, the one that kind of looks like an orthographic cube, I'm going to click the drop down and go to the third button, which is show feature lines with shaded faces. That's just going to turn off my mesh lines. Once again, it's just going to allow me to see the color contour, the blended display a little bit easier. All right, we're going to start out here in the filling results. Like I mentioned previously, the project tree holds all of the input information, but it also will be used to hold all of the output results as well. All right, so down here in the results section, you can find the filling, packing, cooling, and warpage results. We're going to start off in the first result category, which is filling. All right, and the first result here that we see is melt front time. Melt front time is used to indicate how long it took to get from the melt entrance, which would be the top of our gate in this situation, to that location on the geometry. You can see that the red color on our scale indicates 0 seconds. So right on our melt entrance, it took 0 seconds, obviously. And it looks like it took about 2.1 seconds to get all the way to the end of fill, that dark blue color. That's not too important. What I'm more interested in is how the material got from the melt entrance to the end of fill, not necessarily how much time it took. And in addition to that, I'm interested in how the end of fill on the left side of the part filled out as compared to the right side of the part. this is an indication that we call flow balance. To interpret this a little bit closer, instead of just looking at the color contours, I'm going to go into my result interpretation tools, which actually, if we follow the procedure that we've been using up until this point, to the right of the run button is actually the result button, which is going to take us directly over to the result tab. You can just click on the result tab if you wanted to. The first section in the result tab is our animation toolbar, and you can hit the play button to play the animation of the melt front progression. You can pause the animation at any point, and you can actually use this value here to go to a very specific point in the animation profile. Let's say I go to the 90% mark. So we're able to kind of see how that melt is finishing its filling. Pretty reasonable for this part. This part actually is pretty consistent as far as the thickness profile is concerned, as we saw at the beginning of the training. But as far as flow balance, and once again, flow balance is really the comparison of how the melt front gets to this point, or I should say more of when the material gets to the end of fill on the left side of our part to the when the material gets to the end of fill on the right side of our part. In order to adequately study the flow balance, I'm going to go to my VP switch point. The VP switch point is usually anywhere between 95 and 98%. My recommendation, just as a generic rule of thumb, I usually like to go to the 95% mark. 95 is pretty good. The further you can push this and have both end of fills unfilled, kind of like what I have here. You can see that this side over here is unfilled. This side over here is unfilled. That's great. That means I have a good flow balance, especially at 95%. I would say that I have a 95% flow balance. But the further I can push this value and have both end of fills unfilled, the better my flow balance actually is. So if I go all the way to 98%, let's say, you can still see that this side of my part is unfilled, this side of my part is unfilled. So I even have a further flow balance than 95. I would say I have a 98 flow balance, 98% flow balance. And I can continue going as far as I want to. And the better my flow balance is, the more open my processing window is going to be, and the more variable or the more flexible my VP switch point can be. As far as the flow balance is concerned, I'm trying to optimize two different things. The first thing is the pressure loss across my system. I wouldn't really have to worry about flow balance if I had my gate over here, for example, because all of my melt is going to end over here. There isn't really going to be any sort of flow balance that I need to worry about. But if I put my gate over here, the pressure loss to get my material from this location on my part all the way to the end of fill over here is much, much higher, since the flow length is pretty much double that of the current gate location. All right, so I can optimize my pressure required to fill my system in that way. But I can also optimize or at least investigate the presence of pressure spikes. Pressure spikes occur when you have one end of fill, when you have the melt front ending at one side of the part much sooner than the other side of the part. And we actually do have that marginally in this case. In order to investigate this, I'm going to go over into the filling, XY curve, and sprue pressure. All right, so sprue pressure allows us to see, first of all, the magnitude of pressure required to make this part. In this case, I would say that the peak pressure is 95 MPa, somewhere around there. But it also allows us to investigate how the part got to that 95 MPa, right? There could be a high pressure loss in the feed system. There could be a high pressure loss at some region in the part, depending on the thickness profile. And along the way, there can be small disruptions like this guy right here. Up in my result toolbar, I'm sorry, over in the animation toolbar of the result tab, I'm going to use this slider to back up my animation. You can kind of see this dashed line going across my curve. I'm going to back up my animation to just before this pressure spike occurs. All right, at this point, actually what ends up happening is that this upper right corner ends filling. And so all of the momentum of the material that was going in that direction has to transition to either going towards the left side of our part or towards the bottom right side of our part. It's kind of like water rebounding off of a wall. If you've ever seen water or a wave rebound off of a wall, when that rebound hits another wave, you get a big spike. That's kind of like what happens here, or a higher amplitude wave. If that momentum shift goes through the melt entrance, then you're usually going to get some sort of impulsive pressure spike. And actually, in this case, the pressure spike's magnitude, or I'll say the amplitude of this pressure spike, is pretty low. Not really anything to worry about necessarily. It's just a little bump in the pressure requirement. However, if this pressure spike occurs closer to the end of fill or closer to this maximum pressure point, the amplitude will increase. And in most cases, that amplitude will increase above the expected maximum pressure, which first of all will create a very impulsive force onto the machine, which can hurt your machine long term. But second of all, it will increase the pressure requirement needed to make this part, which if that impulsive pressure spike goes over or goes close to the machine maximum, that's really where you can start doing damage, especially over a large number of cycles. If we can get our flow balance anywhere after the VP switch point, which is this guy right here, if we can get the flow balance to occur anywhere after this point, any sort of pressure spikes or any sort of imbalance that happens after this maximum point or this peak pressure will be instantly dampened out because we're no longer holding a constant flow rate condition. We're transitioning to the packing stage. But anything before this point, we are still holding the flow rate constant. Actually, I can overlay the flow rate onto this curve by right-clicking on flow rate and hit add to XY plot. And so the flow rate is constant until this point. And when the flow rate is being held constant, in order to maintain that constant flow rate, any sort of impulsive nature of the melt inside of our geometry has to interact with the pressure, not the flow rate itself. But after this VP switch point, the flow rate becomes non-constant. Actually, it kind of drops to eventually zero or close to zero as the material or as the part packs out. All right, so we really want any sort of flow balance that we get in our geometry to occur, or we want any imbalance, I should say, that we get in our geometry to occur after this VP switch point. I'll say as a rule of thumb, 95% is okay, but the true balance point should be that the maximum or the VP switch point on your pressure curve. Another result that I like to take a look at, and this is actually something you can use to evaluate your cycle time for filling, is the temperature. The temperature distribution in the filling stage can be used to evaluate whether your temperature is increasing over the length of fill or decreasing over the length of fill. You might think, okay, well, the heating source is at the melt entrance, which means that as we progress along our length of fill, that heat should be, or that energy should be released out into the mold. And so our temperature should decrease over the length of fill. But actually, there's a secondary effect that we need to consider as well, and that is the shear heating effect. As the material is compressed through our gate, and as it flows through this thin cross section in our part geometry, the friction of the moving material up against the frozen material, which is on our mold surface, that friction will allow that energy of the movement of the material to be converted into heat. And that will actually tend to increase the temperature of the melt as it progresses. So there's actually this balance that's occurring. Energy is constantly being released out into the mold, but the movement of the material is also converting that energy into heat as well. All right, so there's kind of like a heat generation effect, and then there's a heat release effect. I usually like to call it the cooling effect and the shear heating effect for simplicity. So which of those effects dominates is going to dictate whether our temperature increases over the length of fill or decreases over the length of fill. And unfortunately, we can't really tell which of those is the case just from the surface temperature here. Because we use a 3D solver, this temperature distribution is quite literally the surface temperature distribution on the mold. This doesn't represent what's actually happening through the thickness of our geometry. So we have a couple of tools that allows us to slice open the part geometry and evaluate that temperature distribution a little bit more adequately and a little bit more more of a comprehensive way. The first of those is going to be in the inspection tab, or the inspection section of the result tab. And it's called the clipping tool. The clipping tool effectively just creates a cross section on our part geometry. And you can actually see, if you zoom in a little bit, you can see that temperature distribution from the surface of our part into the core. You can move this surface up and down by simply just left click dragging it. And now I'm trying to evaluate the temperature difference between the gate location and the end of fill. And so maybe I'm going to change my orientation of my plane. I can do so using these little toggle buttons up here. I can use either the XZ or XY directions. Actually, I can use both of them simultaneously if I really wanted to. I find my gate location, cut that in half, and cut it in half one more time, kind of like a quarter. Right, and then we can see how our temperature distribution is changing, or how the magnitude of temperature is changing from our gate location in the core of our part, this kind of like lighter orange color, to the end of fill, which is actually in a more of a darker orange color, which actually indicates to me, maybe, that the temperature is increasing over the length of fill. But there's actually a better way to interpret this, and that's through the button right underneath the clipping tool called the slicing tool. So I'm actually going to get out of here, and we're going to use the slicing tool. So right underneath the clipping tool is the slicing tool. Over in that inspection section of the result tab. Now, slicing tool effectively does the same thing as the clipping tool, just instead of creating a cross-sectional plane, it projects the results onto a determined plane. And the reason that this is a little bit better, I'm going to use that the same planes that I used before, XZ and XY. The reason that this is a little bit better is because I can actually create multiple planes in the slicing tool, whereas the clipping tool, you can only really create one plane in each direction. In the slicing tool, I can create, let's say, 10 planes in the XZ direction and 10 planes in the XY direction. This creates what we call a slicing grid. I can uncheck the show plane checkbox here, make things a little bit easier to see. Now, the entire core of my geometry is really up towards the top side of my scale, obviously, because that's where the hottest material is located. So I'm actually going to decrease the extensive, or I'm going to change the extent of my scale. Since I'm really only interested in the top portion of my scale, I can actually bring the bottom of my scale upwards, kind of like what we did for the thickness distribution earlier. I'm going to left click drag the bottom of my scale upwards. That's just going to allow me to see this color distribution, a little bit more diversity, a little bit more contrast. And we can pretty obviously see from the slicing grid that the end of fill temperature distribution in the core of my geometry is hotter than my gate location, or the gate region. All right, so in this case, I would say that the shear heating effect, the generation created by the heat generation created by the friction of the material, is greater than the heat that was released out into the mold. This isn't a very common occurrence, but is certainly something that can happen if you have too low of a filling time or too high of a filling speed. And so this is a way that you can determine whether you need to decrease your filling speed. Actually, in an ideal world, we would be able to balance the cooling effect and the shear heating effect perfectly. And you could actually get a situation where you have a pretty constant temperature throughout your geometry. That means that the shrinkage rate of your material across your part is going to be consistent. And as I'm going to mention a few times here, a consistent temperature distribution leads to a consistent shrinkage, leads to a minimal warpage. Right? The definition of warpage in Moldex3D is a variation in shrinkage. Wherever I have a change in temperature, wherever I have a change in pressure, that's typically where we're going to see a variation in shrinkage. Wherever we have a variation in shrinkage, that's where we're going to see warpage. All right, so along that same line of thought, I'm going to go into the packing results, and we're going to look at the packing pressure to take a look at how our pressure distribution is laid out across our geometry. We actually don't need the slicing result here, so I'm going to exit out of that slicing tool, and we can just look at the color contour on the surface. Now, when we're looking at this packing pressure, what I'm really looking for is to see how distributed this pressure is. The purpose of the packing stage in our process is to continue to pump material into our geometry to minimize the amount of shrinkage that the material is able to exhibit. Right? The material has some sort of natural shrinkage to it, but if I compress more material or more polymer chains into the geometry than would normally be allowed, then I really combat the natural shrinkage of the material. But it should be noted that this packing effect or this compression effect can only really occur through molten material. Once the material freezes off, you can no longer push additional polymer chains past that area. So when I look at the packing pressure result, what I'm looking for is to see how distributed this pressure is. Being that we're applying the pressure from this melt entrance, I would really want to apply that pressure throughout my entire geometry and have a nice consistent distribution. But actually in this case, what we see is that the pressure is pretty localized to the gate location or the gate area. What this means is that if I were to pack any longer, I'm going to be packing additional material or additional polymer chains into this area of my parts. but that same effect is not happening out towards the end of fill. That means that I'm going to have a low shrinkage at my gate location, which is good, but I'm actually going to have a much different shrinkage value at the end of fill. And like I just mentioned with the temperature effect, any sort of variation in shrinkage is going to lead to warpage. All right, so I really want this packing pressure distribution to be as uniform as possible across my geometry. Not necessarily constant, because the pressure at the end of fill is always going to be zero, and the pressure at the gate is always going to be at the maximum. So it's not necessarily that we need the pressure distribution to be constant or the same color, but we want the gradient to be pretty smooth. We don't want it to just drop super quick from the gate down to this blue color. We want it to be nice and even of a gradient or a change in pressure across our geometry. All right, so like I just mentioned, the packing effect can only occur through molten material. And so our next step here is to evaluate where the molten material is across our geometry. All right, so in addition to looking at this pressure result, I'm actually going to use a tandem display or a compare display to show the pressure result side by side with the molten core result. All right, so first things first, before I introduce the new result, let's go into our compare mode. So under the result tab, all the way over towards the right side, you have the compare button. This will implement two windows. This is great for comparing two runs to one another. If I have two different sets of inputs and I want to compare those the outputs from those input profiles to one another, this is a great way to do that. But it also allows us to put these two results of the same run side by side with one another. All right, so on the left side here, I'm going to have the packing pressure. And over on the right side, you can left click over in the right panel to make that your active window. And I'm going to change that to packing and molten core. All right, once I have those two results, I'm going to turn on a couple of syncs just to make my life a little bit easier. The first one is sync rotate. That'll make it so that I can rotate both of these simultaneously. And the other one is sync zoom. It just makes it so I can evaluate these two parts in the same orientation simultaneously without having to kind of rotate both of them independently. All right, so what the molten core result shows us is where the molten material is in our geometry, or all of the material above the freeze temperature. You can see the bottom of our scale here is 150 degrees Celsius, which is our freeze temperature of this PCABS material. All right, now if we recall from the filling results, remember that the highest temperature material in the filling stage was at the end of fill. So it actually makes sense to me that that there is still molten material at the end of fill. And we are consistently pumping material out of our melt entrance to pack out our geometry. So it also makes sense that there's molten material around our gate location. All right, so if there's material at the end of fill that's still molten and material at our gate location that's still molten, why can we not get the material from our melt entrance packed out all the way throughout our geometry? Why don't I see a consistent gradient across my parts? And the reason is because of this area right here, kind of like the intermediate area between the gate location and the end of fill. This actually almost always happens with shear dominated flow, or when we have the shear heating effect that is greater than the cooling effect. The intermediate area is the first place to freeze off. That isolates the molten material at our gates from the molten material at our end of fill. I can still pack out this region, but I don't have a pressure source to pack out that location. And so although this material is still molten and has a high shrinkage rate, we're not combating that with any sort of pressure from our gate because it's isolated from the gate. All right, so in this situation, we actually end up getting an isolation where the material at the gate location is going to be packed out very, very well, but the material at the end of fill, even though it can be packed out because it's still molten, it is not going to be packed out because it is isolated off from the gate location. All right, and then from this, I can actually go into the volumetric shrinkage, get out of the compare mode. We only need the volumetric shrinkage result here. You can just click on the compare to get rid of that. We can then look at the volumetric shrinkage profile across our geometry. You can either use the slicing grid, or actually you can just look at the surface of the geometry. This is a pretty good representation of what's happening across the geometry, even though the magnitude is slightly different through the thickness. The general gradient is pretty similar. And so I can take the maximum of my scale down, and we can see how different the shrinkage rates are between the left-sided or the end of fill regions on my part geometry and the gate location. Because the gate location is so packed out in this situation, because it's isolated off from the rest of our geometry, instead the shrinkage rate is extremely low at our gate. Whereas the shrinkage rate is extremely high at our end of fill because it's high temp. The end of fill is high temperature. It took a long time to freeze off, and it's not very well packed out because it got isolated off from our gate. All right, so then from here, we can then move into the third section of our results, which is the cooling section. This allows us to evaluate how adequately our cooling system was able to remove heat from our part geometry. And in addition to that, it allows us to evaluate where we can make any sort of changes in our cooling system to get a more uniform temperature distribution across the surface of our geometry. Kind of like what I mentioned in the filling stage when we looked at the filling temperature through the thickness of our parts. In the cooling stage, we're more interested in what's happening across the surface. And in order to combat or in order to minimize the warpage that we get on our part geometry, I want to make the surface temperature as uniform as possible. If I have uniform temperature, I have a uniform shrinkage across the surface, which means I have a minimized amount of warpage. All right, so the first thing I'm going to look at here is the temperature distribution in my part geometry itself. I should say across the part geometry, not in the part geometry. All right, I don't need to use any special tools here. I can just look at the surface temperature across my parts. All right, because the temperature is highest through the thickness of my geometry, most of the temperature distribution on the surface is going to be towards the bottom of the scale. So kind of like some of the other results that we've used, I'm just going to left click drag the maximum of my scale downwards so that I can see that temperature distribution a little bit more adequately. If you have a situation like this where you get like a splotch of material that seems to be not colored at all, just means that it's outside the extent of your range, and you can just increase the maximum a little bit. All right, so we can see in this situation that there's a hot spot on the top side of the part right here. You can kind of see that the temperature is a little bit higher. You can also see that the temperature is a little bit higher down here on the bottom side of the part in this little channel. And sometimes I also like to show the cooling channels as well. So I can go over to my model tree, which again is that second tab over on the left side of your screen here. and I can turn on my cooling channels to really see what the layout of those cooling channels or how that cooling layout of the cooling channels is corresponding to the temperature distribution that I see. I don't really care about the temperature on the cooling channels themselves for the time being. I care more about just kind of visualizing where these hotspots are happening as they relate to the cooling channel layout specifically. So we can see that right between these two cooling channel, kind of like the inlet and outlet for this conformal line, we can see that the hotspot occurs right between those two. I think this highlights a really common misconception in tooling design, and that's that the cooling channels act as a magnet for heat transfer. The cooling channels don't act as a magnet for for heat transfer. They just remove the heat from the mold directly where they are located. All right, the heat actually is going to accumulate in locations on the part where there's not a cooling channel, and eventually that heat might be pushed out to the cooling channel, but it's going to accumulate faster than it pushes. All right, so it's very common for even a conformal system like this to have a hotspot that occurs just because there's some feature on the geometry that is not being adequately addressed. And the same thing actually occurs right in here. You can see that there's a little pocket or a little corner where the heat can accumulate, and the cooling channel that I've created here does not directly address that pocket. All right, so to improve this cooling system, maybe I just drop this cooling channel a little bit closer to the surface of the part. Not sure how possible that actually is because of the actions that might be necessary for these windows or these clips on the geometry. This guy I might be able to create like a baffle or some sort of maybe put in an insert that has a higher thermal conductivity to remove that heat a little bit quicker or a little bit with a higher efficiency. These are different cooling tactics that you could look towards. The other result that I like to look at here is the mold temperature difference. Get rid of the cooling channels here. Mold temperature difference is a really cool result. As I mentioned, the temperature distribution across our geometry is going to imply a variation in shrinkage, which can eventually lead to warpage. And so the effect that we like to look at here is called the PVT effect, which allows us to determine the impact of having the temperature higher on one side of the geometry versus another side of the geometry. That's not specifically where the PVT comes into play. The PVT comes into play across the entire geometry, but as it applies to cooling specifically, if I were to think of having a flat plaque, if I have one surface that's a little bit hotter than the bottom surface, this is like a 10 degrees difference, then I'm actually going to see that the material on the top side shrinks inwards a little bit more than the material on the bottom side. And that actually pulls the material or the part in this situation into more of like a smiley face configuration. All right, so if I have a large delta in temperature between the top surface of my part and the bottom surface of my part, I can actually start to see the warpage quite a bit. And that's really where the mold temperature difference effect is going to come into play. Mold temperature difference just tells us the difference in temperature between the top side of our part and the bottom side of our part. So when we're looking at, for example, the temperature result, get that temperature down a little bit. We can see that the temperature on the top side here is quite low relatively. You can see that a lot of the temperature here is like a greenish color, where this is like a bluish color, but on the bottom side we have red. So down here we have a very high temperature. On the top side we have a relatively low temperature. And so I would expect that there's a high mold temperature difference in that area. And as it turns out, they certainly do. All right, so mold temperature difference tells us the absolute difference between the top side temperature, the A side temperature, and the B side temperature. And so this really allows us to adequately evaluate not only where there's a problem in the cooling system, but ultimately how that problem in the cooling system is going to impact the final shape of the part, or where the part is going to be most prone to warping. Now, there's actually an interesting way that you can interpret this result. The tolerance that we like to use is 10 degrees Celsius. We'd like to have every major region of our part geometry to have less than a 10 degrees mold temperature difference. And so actually what I can do is just change the maximum on my scale to 10 degrees Celsius. You can do that by just double clicking on the maximum value here. All right, that's going to change the display quite a bit, I'll say. Any region that is currently not colored is outside of that tolerance. And this is a really good visual indication of what regions on my part are very prone to warping based on the current cooling layout. All right, so let's evaluate this a little bit closer with this part geometry specifically. We see that this region has a really high mold temperature difference. We expect that because there was a hot spot on the bottom side in this area here. We also saw that there's a hot spot in this area on the top side of the part. So it's not necessarily surprising that there's a discrepancy or that this area is outside the tolerance. But we actually do see a pretty important area of the geometry over here on the left side that is also outside of that tolerance. I'm going to look at this result in tandem with the cooling temperature, just so I can evaluate this a little bit closer. All right, so over on the left side, I'm going to have mold temperature difference. Over on the right side, I'm going to have the cooling temperature. I'll drop the extent of my scale, just like I did previously. Okay, so we can see on the bottom side, oh, well, there's not really that high of a temperature. I mean, maybe a little bit high of a temperature, but nothing too notable. Definitely as compared to over here, not too notable. But actually on the top side of the part, you can actually see that the temperature is significantly lower than the rest of the geometry. And this actually highlights something that's very important. We're not only looking for the hot spots across our geometry. Hotspots are easy to identify because that's where the temperature is going to be the highest. But we're also looking, we're primarily looking for where the temperature is different significantly different between the top side of the part and the bottom side of the part. The PVT relationship doesn't really care whether this is a hot surface and a cold surface, or a medium surface and a really cold surface. It just cares that there's a difference in temperature between those two surfaces. So we could actually get a situation where we are overly efficient. The efficiency is too high across this surface. If I show my cooling channels one more time, we actually see that the cooling channel gets pretty close to the surface of my geometry here. We could actually get too much efficiency of cooling. It is possible. Pretty rare, I'll say, but it is certainly possible where you get a significantly different temperature between the top side and the bottom side, specifically because there's too much efficiency on the top side of my part. All right, so all of that leads me into the warpage analysis. So in the filling stage, we evaluated the temperature distribution, which is implied by how fast the material was feeding through my part geometry. We evaluated the pressure distribution in the packing stage, which allowed us to see how the uh, packing effect or the compression of material into my geometry is combating the natural shrinkage effect. And then we also looked at the cooling temperature distribution to see how the cooling system is affecting the temperature distribution across the surface of my geometry. All three of these effects are fed into the warpage analysis and are ultimately going to indicate how the part is changing from its original shape. For that reason, it's highly, highly recommended to look at the filling, packing, and cooling results before looking at the warpage results. One of the most common mistakes that I see from a lot of users is that you'll run the warpage analysis, you'll go straight to the warpage results, and instantly, once you look at the displacement, you're going to be biased and you're going to start looking for answers rather than having the answers or even having questions coming into the warpage result and being able to answer those questions through the warpage results is so much more practical and so much more useful than creating questions from the warpage results and then trying to answer those through the other results through filling, packing, and cooling. So it is one, it's much more efficient, it's much quicker to answer questions in warpage rather than creating questions in warpage. And second of all, it's more effective. You will always be able to understand the warpage a lot better if you've already looked at the filling temperature, the packing pressure, the cooling surface temperature. You'll be able to understand and anticipate what's going to happen in the warpage results. And if what you see in the warpage is different from what you expect, now you can have a more educated path as far as how you can interpret or how you can investigate what are the true causes of that warpage. All right, so that being said, the first result that we see here in the warpage results is total displacement. Total displacement indicates how far each node moved from its original location. Very importantly, the scale over here on the right side goes from 0 up to whatever the maximum is. It doesn't go into the negative range. And because of that, this total displacement does not ever give you a direction as far as how this material is displacing or how these nodes are moving from their original location. This is 0.972 millimeters of movement, but is that movement outwards? Is that movement downwards? Is that movement inwards towards the center of the part? Am I shrinking? Am I warping? This doesn't really tell me what direction these nodes are actually moving. To get a good indication of what direction those nodes are moving, you could use the axial direction displacements. So we see the X, Y, and Z. In this case, the X direction is our parting direction, so it's going to be not too useful. So I'm going to use the Y displacement just as an example. You can see on the scale that we have a positive side and a negative side. All right, if we look at our axes, we can see that the positive Y is towards the right side of our screen, as I have it oriented here. So all of the nodes on the positive side of my Y displacement result are moving towards the right side of my screen. All the nodes on the negative side or the blue side of my result scale are going to be moving towards the negative Y direction or the left side of my screen. All right, so that's how you can evaluate this result. It effectively just means that the part is shrinking. That's what you can get from this. It's not usually necessary to go into the X, Y, and Z displacements, but if you want a confirmation of what's actually happening, that's how you would interpret those results. So the total displacement is just a totalization of the X, Y, and Z displacement directions. And so that's why we don't see a negative side to the scale. So then the question becomes, all right, well, how do we visualize uh, which direction or how these nodes are actually moving? And that's going to be through the deformation function up here. Right under the warp section of the result tab, I'm going to go to deformation. All right, we'll see the deformed mesh as compared to the original mesh. You can scale this if you'd like to. I can use like a 10 times scale factor just to exaggerate the warpage and be able to see it a little bit easier. All right, pretty cool. Now, if I look at this side of my part, okay, we see a lot of movement in the kind of towards the center of the geometry in the Y direction. We don't see a whole lot of movement in the X direction, the out of plane direction. And we don't really see a whole lot of movement, maybe a little bit towards the right side in the Z direction, but really not too much there. So I would say that this is mostly just linear shrinkage. Right. So there isn't really too much deformation happening here. It just kind of looks like this is all shrinking towards the center of the part. All right, so if we go down to the bottom side, oh, we can actually see that this is very almost very obviously, just instantly looking at this is very obviously warping. And that brings up a very important point that the warpage results that we see here, this is total displacement, not total warpage. Total displacement is actually a combination of shrinkage, of linear shrinkage from the material, and differential shrinkage, depending on what happened during the process or what happened during the cycle. All right, so even though the two colors here on this side of my part and this side of my part are pretty similar, you can see that they're both kind of on that red side of the scale. This side is displacing almost purely because of linear shrinkage, whereas this side of my part is displacing almost purely because of warpage. All right, so how do we discern between the two? That's actually where the mold compensation comes into play. All right, so the mold compensation, we can input the material shrinkage value. You can get this value usually from your material supplier. I'll let you guys know that the PCABS we're using here has a linear shrinkage of 5 thousandths of an inch per inch, or 0.5%, 0.5. I'm going to use an isotropic compensation, which means that the 0.5 is going to be applied in all three directions automatically. You can apply anisotropic if you have that information available at your fingertips. You can actually obtain that from the simulation. If you look over in the log file, it'll give you those three values. And once we apply that compensation, we actually get a very different color distribution. You can see that the left side of my part is pretty much not displacing at all, which is an indication that the compensation that we applied took out pretty much all of that displacement. Means that it was all linear shrinkage, or mostly linear shrinkage, I should say. Whereas the other side of my part is still on that red side of that scale, indicating that this is purely, or as it exists right now, this is purely warpage. All right, so it's just a great way that you can discern between the linear shrinkage and the warpage across the geometry. You can apply the material shrinkage value. You can see that distribution change quite a bit. All Now, a very important feature that has been implemented in Moldex3D 2024 is this new tool called Export Deformed Model. Export Deformed Model, actually, this function has existed for quite a while, but the functionality of this tool was not nearly as high as it is right now. Oh, actually, I don't have the option. I don't know why I don't have the option here. Oh, because the simulation was ran in a previous version. Oops. That's okay, though. In 2024, you're actually going to see a new option to export the deformed model as a step file. And that's an extremely useful tool. Instead of just looking at the results in Moldex3D, I can now take the results of Moldex3D over into a mold file and start designing around that. Right. So instead of maybe taking the shrinkage values that we get from the simulation and then just applying that as a blanket shrinkage value for your model to apply some sort of windage, you can actually export the model from Moldex3D. You can export a 1x deformation, which would be a shrunken part, but you can also actually apply a negative value here. You apply a negative scale factor. That means that now the part is going to be expanded or increase in size, kind of like a windage. And then you can plop that, because it's a step file instead of an STL. Previously, it was just a point cloud or an STL file. Now, because we can export the step file, we can actually plop that directly into our mold design and then just start designing around it. This is an extremely useful tool, and I urge anybody to begin using it. I think it is an extremely important step for us to start moving into more of the intelligence realm of molding, and really allows us to get a nice feedback loop between the simulation and the outputs from the mold, or even the inputs to the mold. There's a lot of feedback loops that are closed because of this exporting of the step file. We're extremely excited to see where a bunch of users start to take this, and also where we start to take this from a development standpoint in the future. Now, a couple of other tools that you can use in Moldex3D for the warpage results. The first one is the distance tool. Over in the measurement section of your result tab, the distance tool on I guess on the surface, the distance tool really doesn't seem to do a whole lot. I can just click 2 points and voila, it gives me the surface. But if I hit save and close, it gives me the original distance. It also gives me the deformed distance. And more importantly, it gives me the linear shrinkage between those two values. All right, so if I want the linear shrinkage in a custom direction or a custom axis, I can do that pretty easily. And it also, if I want to evaluate a particular dimension across my geometry, let's say I want this corner here and this corner here, save and close. All right, we see that the deformation is pretty high, but does that lie within the tolerance that I'm given? I can really use this to determine that more directly rather than just looking at the color contour, which just tells me the relative displacement. All right, the last tool I want to show off here is measuring face. Measuring face allows us to extract information from a particular surface, but it also allows us to isolate a particular surface from the rest of a result. This isn't only for warpage. It does apply pretty well for warpage. If I'm thinking of something like, let's say, flatness or relative flatness, I can now isolate this surface and see how much it deformed. Assuming that it was a flat surface in the geometry, we can really get an indication of how how much displacement there was in the different regions. Now, this surface wasn't ever completely flat, so it makes sense that there's quite a bit of deformation, but you can utilize it in that way. We also have a flatness tool. You might have already seen it. There is a flatness tool that does a similar thing. It just creates a flatness plane and measures the deviation. You'll see a pretty similar color distribution from those two results. Do it real quick. Flatness. Save and close. You can see a pretty similar color distribution. It's inversed because of the fact that it's more of a deviation from the flatness plane. So the colors themselves look pretty different, but the actual contour or the actual information you're getting from these two tools is very similar. Now, all of these measurements show up over in your model tree. You can toggle those on and off if you'd like. You'll also see that some of these probe nodes will be created from the distance categories or from the distance measurements. You can turn those off as well. All right, and that's going to wrap things up for this Moldex3D standard online training. I really do appreciate everybody for coming out and spending a few hours to learn a little bit more about Moldex3D. Just as a bit of other information, you can follow us over on LinkedIn to see what events are coming up. We have a lot of events that we take part in every year. We do host a symposium in the April to May timeframe, which is just a users meeting. It allows all of our users to come together to share all of the information that they've learned. But we also participate in a lot of the conferences, and we create our own molding innovation days where we start to share a lot of the information that we are developing or a lot of the features that we're developing for the future versions of Moldex3D. And then I've referenced this a few times in this training, but you can also head over to our YouTube channel, Moldex3D North America, and you can check out all of the videos that show up there. I've compartmentalized a lot of the information that I've shared in this training there. So things like the material process, the result interpretation, all of those are different videos that you can kind of view along your path to learning a little bit more about Moldex3D. And then finally, you can send an email to cases.us@moldex3d.com. This is our general support hotline, where you can either speak with me directly or you can speak with one of our other support staff. We have a bunch of experts that will help to answer any questions that you have about the software. Anything from getting started with Moldex3D all the way to using advanced molding modules or correlating molding studies. We have the capability to do any sort of correlation or help in any way that we possibly can. All right, thank you everyone once again. Hopefully we'll see you at one of our future events or one of our future training sessions. We have a lot of advanced training sessions. You can check out our LinkedIn to see those as well. We once again thank everybody for coming out and spending a few hours with me and my team to provide all this information to you guys. And we're actually going to go into a question and answer session. So if you do have any questions, you can stick around, ask those questions in Teams. But if you do want to get going, thank you and have a good rest of your day. All right, awesome. So I had a question about the venting a little while ago. So let me go back to this model here. I'll just show real quick how to implement a venting profile. It's actually really quite simple. I'm going to get rid of my cooling channels and my mold base. Get rid of these guys as well. Now, the venting can be applied on the surface of the geometry. but it can also be imported as well. So if I wanted to use a feature on the geometry, like my parting line or something like that, that should be embedded on the geometry and I can use that. You can also use the mesh elements as well, which is interesting. So to start out, I'm going to go into the boundary conditions and over into venting. All right, now it asked me to select curves. The curves can be one of three things. It can either be a feature line, in which case the selection will spread to the rest of that feature line. You can use shift select an entire feature line. So if I wanted to choose the parting line, I could do so in that way. You can also select individual mesh lines like this. More of an approximative approach. But also I can use, let's see, tool, line, and I can say, select here. All right, so I can create a line across the surface of my geometry. Oops, boundary conditions, venting. And I can actually select that line as my venting profile as well. And you don't have to create these lines in Moldex3D. You can actually import these lines as well. So if you have the venting or if you have the parting plane established in your mold system, but that isn't directly implied on the part geometry already, then you can import those lines directly into Moldex3D and then select those lines for your vents. They don't have to be used in the analysis in any way other than just to establish the venting profile. Now you do have to be kind of careful though. If you, like I said, for venting, once you apply one venting boundary condition, that means that the air can no longer escape ideally from the rest of the part. And so if I only apply a venting boundary condition on this side, I will 100% of the time get a short shot because the air cannot escape from this side of my part. All right, so you do need a complete venting profile across your entire geometry, not just the venting profile for the location that you're interested in. Just a small note. And then the size of your vent is going to be applied here. So I'll say like the length dimension, the length of your vent is this line that you've selected. And the W dimension is the land of your vent or the distance from your vent out to the main vent channel. Kind of like this dimension. And then H is the thickness of your vent, the height of your vent. All right. It's not going to be created as a solid geometry or anything like that. This is more of a consideration for the numerical solver. But yeah, so the venting profile will be applied in the simulation. You'll be able to see where the air is having trouble escaping from the part. Like if my melt front kind of comes down and closes off this feature, I might get a short shot down here if I don't vent it properly, or maybe on the bottom of these bosses or whatever have you. So yeah, really cool, really interesting case studies that we've done with the venting simulation. It's actually proven to be quite accurate. All right, does anybody have any other questions that they'd like to ask? You can shoot those over in the chat and I'll be happy to answer them. Does the simulation need to be rerun after the event is added? Yes, this is an input, not necessarily a change to the outputs. So yeah, it's you can consider it more of like kind of like the same as changing the cooling layout or changing the runner layout. It's a change to the geometry, so you would need to rerun the analysis. Yep. Can we characterize both base material and colorant? Whenever we characterize a specific grade of material, we characterize it as a complete matrix. We do not characterize the two, the different additives. We don't characterize those separately. We characterize them all as the mixture that you would experience in the molding process. So we could characterize both of them separately, but it wouldn't help in the simulation because we can only implement one material for each analysis. So we would always characterize the base material with the colorant included. You could characterize the base material and the base material plus colorant. You could characterize those separately to see the impact of the colorant, I guess. But you would need to characterize both of them. Yep. All right. If there's no other questions, then we'll end the session here. Like I said, if you do have any additional questions after this training, you can shoot an email over to cases.us@moldex3d.com, and we'll be happy to answer any questions that you have along your way in your Moldex3D journey. So hopefully we can speak to you at some point in the future. But for now, have a great rest of your day, and hopefully we'll see you at one of our future Moldex3D events, or hopefully we'll hear about you from our support. Thanks, everyone.